which by itself is an insulator in its normal form. Well, not normal form, but in its refined form. It's an insulator. Ooh, it doesn't conduct electricity. We change the atomic structure, make some of it positive and some of it negative. And so we have two different polarities of silicon, so bipolar. Junction, remember, it's the PN junction. It's the thing that we're testing in the diode between the type P silicon and the type N silicon. Represented schematically by that bar. Remember I mentioned to you yesterday that all semiconductors have a bar. There's a diode semiconductor with a bar. Here's a transistor semiconductor symbol with the bar. In the case of the transistor, remember, it has two PN junctions. Remember that this is the emitter, the collector, and the base, right? So there's a PN junction between the base and emitter, and that's the first thing you tested. And then you kept the red lead on the base and checked between the base and collector. There's the other PN junction right there. So that, remember I mentioned to you the first day of the class that the schematic symbols are kind of telling a story. It's either what it looks like or what it does. And in this case, we can see how it's built. It has two PN junctions between this one and this one and this one and this one, and that is the PN junction. So, there's kind of a logic to the way the symbols are set up. Anyway, so these are, and they're transistors, right? Remember, transfer resistor is how they got the term. Bipolar junction transistors. So these things were invented around 1950, I think. The bipolar junction transistor was invented around 1950. The actual first transistor was invented in, I think, 47. It was a different kind of transistor made with a different kind of semiconductor material called germanium. So the very first transistors and transistor radios and things like that were these germanium transistors. You don't really care for what reasons, but they weren't as good. They weren't as rugged. There's a bunch of reasons why they worked, but they weren't as good as the thing that superseded them, the thing we use now. The junction transistor. Because the bipolar junction transistor is super rugged. It's just a hunk of silicon. It's one piece of silicon treated with different chemicals, if you will, dopants, to make it positive or negative. But it's a solid piece of rock. Silicon is, like a rock, like this. So it's a real rugged device. So anyway, since 1950 or so, this transistor has been our best friend. It enables us to put the Voyager spacecraft out there, to land on the moon, to, do all the modern stuff in the modern world that we can do. However, there are a couple of limitations to the bipolar junction transistor. One of which is that, remember I said, let me go back to how it works for a second here. Oops. So remember we have the emitter, the collector, and the base. And I said, hey, all we have to do is put like 0.6 of a volt on the base and the collector and emitter connect together. I sort of lied to you. It's not a perfect connection. No matter how much the transistor is turned on, if you remember, we discussed how a transistor works. Starts at infinite resistance, and the more juice you put on the base, the less resistance there is between the collector and emitter. What I said to you, and the big lie is, not big lie, there's a lie here, that it connects collector to emitter. It doesn't. It's not a perfect connection. No matter how much I turn this transistor on, even if it's like on, as much as it can be on, and we actually have a term for this, you don't really have to know. We say that the transistor is saturated. When a transistor is saturated, it's just on as much as it can be. There is a small amount of resistance between the collector and emitter. And that's problematic for a couple of reasons. One of which, it becomes part of an RC time constant we talked about before in some situations where you want to pass current through the transistor and charge up something else. It's going to take a little bit longer for that to happen. But way more importantly, remember again how resistors work. anytime you run electric current through any resistance, not just a component called a resistor, it generates heat. That's how it works. The electrons are bumping into stuff and it generates heat. So that's the problem. And that's why if you look at all of our older games, the power supplies have big heat sinks on them, don't they? Like giant ones on the audio regulator board that's for some games, and well, any of the power supplies. They have these big, giant anodized aluminum heat sinks. Those are real expensive, and there's a limit to how much heat that they can actually dissipate. Transistors don't like to run real hot. You have to heat sink them. So it's like a little heater inside the transistor, again, inside the bipolar junction transistor, and that's sort of an issue. But even more importantly, they're kind of slow. A bipolar junction transistor is limited as to how fast it can switch on and off. And that wasn't a problem with older stuff, really, older electronics. We're going to talk about it today that kind of work on 60 hertz, 60 cycles per second. That's nothing. But modern electronics works much faster. I mentioned to you before that, well, things plugged into the mains might be working off of 50 hertz. This might be 50 kilohertz. And bipolar junction transistors they're just not fast enough. It just takes a certain amount of time to move electrons around. Even though the little chip inside is this dinky little thing, they're not really moving at the speed of light. They're bumping into each other, and by the time the electrons move around and do their thing, it just takes too much time for that to happen. So the thing that you have in front of you is the other kind of switchy device, and it's known as a MOSFET, M-O-S-F-E-T, a MOSFET. It happens to stand for metal oxide semiconductor. Wait, we're only halfway through the name of the thing. Metal oxide semiconductor field effect transistor. Wow. Starting with any transistor. Metal oxide semiconductor field effect transistor. That is the name of this part. Hence, we refer to it as a MOSFET. So let me draw the schematic symbol for the MOSFET and kind of let's compare the two. So the symbol for the MOSFET, and there's some variations of this for sure. The symbol for the MOSFET looks like this, more or less. There's one in your book. There's an article in your book about it. It looks just like a transistor. It's in the TO220 package, but the package is just a package. What's inside there can be a regular transistor, or it could be a MOSFET. It could be a bunch of other things, as I'm going to show you later on today. Because it is a different part, the leads do have different names. The thing that we used to call the emitter. Sorry, let me just draw the position of the leads. Hang on one second. Remember, they're in alphabetical order in a bipolar junction transistor in a TO220 package: base, collector, emitter. And remember too that the center lead inside is connected to the metal tab on the top if it's metal. In this case, it's plastic, isn't it? But some are metal, some are plastic, making the tab also the collector. So it's the same exact package, but the thing inside is completely different. The thing that we used to call the emitter is now known as the source. It's called the source. I don't really think about what it means, but I mean, if you compare the two, the transistor has an emitter. What's it doing? It's emitting something, obviously. What? Electrons, I guess. Maybe I'm wrong. I don't care. It's just called the emitter. This is the source of something. What? electrons, I guess. I don't know. I don't really care. It's just really to identify, in this case, the right-hand leg of the device. It's just called the source, and that's all I really care about. The thing that we used to call the collector is now known as the drain. To me, these two things kind of mean the same thing. I mean, one is collecting something, one is draining something out. I don't know. They're just two different names for the same thing as far as I'm concerned. And the drain is the center leg. And also, if it's a metal tab, in this case it's not, would also be the drain. And then over here, the base, remember the base is the controlling element. It turns the transistor on and off. And remember, it takes 0.6 of a volt to turn on the transistor or so. This is now referred to as the gate. The gate. Conceptually, it's like opening a gate and letting the current go through. That term gate is a real common term, by the way, in the world of electronics. There's lots of things that have an input called the gate. There's an article in your book about, in the textbook, I'm not going to cover it in the class, about something called a thyristor. It's a different kind of a switch. It's the kind we use for alternating current. And its control element is called the gate. So in this case, we have this thing called the gate. Anyway, and the gate in the MOSFET requires 5 volts DC or so to operate. The regular bipolar junction transistor, it's just 0.6 of a volt. In this case, the gate requires about 5 volts to turn on the MOSFET. Now you may at first think to yourself, oh wow, it requires a bunch more voltage, that sucks. But in fact, that's a really good thing, because the integrated circuit that you'll see it's going to be connected to puts out 5 volts. That's our normal voltage. That's the voltage for the power supply for the chips. As you know, we talked about it, is 5 volts and like that. So it's just 5 volts. And yesterday you said you tested with the sample parts. If you happen to put the MOSFET in there, it would have said MOSFET, and it would have said that the turn-on voltage is somewhere around 3.6 volts. If you want to, you can try that today. You'll see what I mean. So it really only takes like 3.6 volts to turn it on, but we give it a good solid 5 volt signal just to make sure it kind of really turns on. So, and that's the gate, the far left hand. So it's gate, drain, source instead of base, collector, emitter. So it's not in alphabetical order anymore, but function for function, it's the same thing. The base or the gate, they do the same thing, and so on. So MOSFETs come in 2 different polarities. A MOSFET may be known as an N-channel FET, N-channel, or it may be a P-channel. Just like we had, remember, NPN and PNP, and of course this one is an NPN transistor. And I mentioned to you that NPNs are more common than PNP transistors in the world. They're more reliable. We use them for power control and stuff like that. Same thing here. Yes, 2 different polarities of MOSFETs do exist. You are extremely, way more likely to see N-channel FETs, which is what I've drawn there, in the real world. Yes, P-channel FETs exist. Typically, when they do exist, we don't ask them to do anything very difficult. It has something to do with the manufacturing processes. I really don't know. I'm just a parts changer. I just change the parts and then it works. So what I've drawn here is an N channel. If this had been a P channel, the arrow would point in this direction. So it's kind of the opposite of this one. This one, the NPN pointed out and the PNP pointed in, if you recall from yesterday. In this case, the P channel points out. And you might never see this symbol in your life. You might never see, we try not to use them in places where they'll fail. That having been said, if I'm a technician and I see something, I don't care what the thing is, what kind of piece of equipment, and I see some N-channel FETs and some P-channel FETs, and it's pretty obvious that they're doing the same thing just with different polarities, and I have a failure, the first thing I'm testing is the P-channel FETs. I'm never disappointed. It's the same thing I mentioned to you yesterday about XY games, how the PNP controls the left half of the screen and the bottom half, and it's very common to lose one or the other, or even both, and just have like a quarter of the picture. It's the P and P transistors. Yeah. Anyway, so this one is a P channel. Let's go back to our normal N channel. And the way the MOSFET works is extremely simple. When you gate the MOSFET, turning it on is called gating it, which is weird because we don't say when you base the transistor it turns on, but we do say when you gate the MOSFET, turning it on, the drain and the source are connected together. And this time it is a perfect connection. It's just like a wire, and it's fast. It's nothing's instantaneous in the universe as far as we know, but it's really super fast. Oh, I forgot to mention the reason that it's called either N channel or P channel is the way it's constructed. Inside there's that little chip of silicon, same little chip of silicon I showed you inside the diode, basically just a little chip of silicon. And the way it's built is that it has an actual channel between the drain and the source. And the channel can be made of type N silicon, which it is mostly, or type P silicon, so hence N channel and P channel. And the gate somehow magically, in what's called an enhanced MOSFET, when you put 5 volts on the gate, it makes a field, an electrostatic field, I guess, that turns that into a wire. The channel itself is just turned into a wire. So instead of moving a bunch of electrons around back and forth, which is the thing that makes the bipolar junction transistor really slow, well, not really slow, but slower, now the gate energizes the whole channel all at once, or as fast as it can, and it becomes a wire. So they're really super fast. And the other deal is that because it is an almost perfect connection, I mean, there's some resistance there when it's turned on. It's measured in milliohms, I think. I'm not even sure, a few milliohms or something. Remember, when you run electric current through a resistance, it generates heat. Well, because there's no resistance now, it doesn't generate very much heat at all. So, for example, on a power supply like this, there's a MOSFET there, and you can see it on this heat sink, but it's not a very big heat sink. In the older vintage games that you're working with, where there's the big heat sink, it takes the place of that. That little heat sink, for scale, here's my pen. So it's a little heat sink. Takes the place of that giant finned aluminum heat sink. It's one of the reasons that these kinds of power supplies, which we're momentarily going to talk about, or later we'll talk about, are so much cheaper to manufacture and smaller. You just don't need a big heat sink if it's not generating very much heat. So it's super fast, doesn't generate heat, and that's what everything is. Not everything, but that's mostly what we use now, are MOSFETs. We use them in modern electronic pinball machines to control the solenoids. We use them in power supplies. They're used in your phone. They're used in computers. And when they say that a CPU has 3 billion transistors, they're MOSFETs. We can make them microscopic, like tiny, itty-bitty things. So let's test the MOSFET, and this is the only time you will have to do this. You will never have to do this complete test again, ever in your life. So pull out your meter, put your meter on the diode test, please. And make sure you have the MOSFET in front of you, not the TIP31. So you never have to make this test again, and you'll see why. You'll see why after we're done with it. So I'm just going to talk you through. Oh, I'll wait till everybody, my new students, open their meters up. Oh yeah, she'll need batteries.
Yeah.
There you go. Oh, well, let's just take a couple minutes to let them get their meter set up. Thank you, teachers assistants. Oh, that's right. You have to unscrew them. You brought your own.
Yeah, it's awesome.
Is it really? Oh, well, you're such a complainer. What the heck? Jeez. What do you think? You wouldn't share your Mosfet with your partner. You might want to reconsider this relationship. That's pretty selfish. I don't know about that, Miss Bunny. No pressure. We're just waiting for you. We're all waiting for you. No pressure.
And I'm watching.
I'm watching. Dickie, can you get the 360 cam over here?
That's what I do.
Oh, it is. Yeah, it is. I'm right on the edge, so I must be super distorted at this point.
It's fine. What?
It's an amazing spherical lens. It's just a fantastic device. I was seriously thinking about getting one. I really want to kind of do travel logs. I'm on the road a lot, and people are interested in the weirdest things. Oh, here's my plate of yakisoba noodles in Tokyo, and you got like 50 guys looking at me yakisoba noodles. Yes.
This is okay.
It's my opinion.
Capacitors or ESR?
Capacitors.
Less useful than testing ESR. Where's the slide?
Here.
Oh, that's great, isn't it? Oh, that's super.
It can
I
also
love that.
It can also do oscilloscope features. That's 1,000 hertz.
Killer.
There's also a keychain for it. It's not much, but for something you can use camera.
That's cute. That's cute as
The
heck.
keychain brand is also really fun. It's just like this large as a circle, and you can pull out the wires. Yeah.
Oh yeah, the older one. Yeah. This is the new version of that one.
Oh my.
This one, you
And have you seen the new one?
I got this one.
That's the nice one.
That's all it is. And uses the 100.
Yeah.
Well, it's resistance.
Yeah.
Oh, my.
Multimeter and everything.
Links. Send me links.
It's called a Focus. They're made in the US.
Spell it?
Focus.
P-O-K.
Oh my god.
Yes, it's
Okay. Thank you.
Enjoy it.
Thank you very much for your educational. All right, here we go. So set your meter on the diode test setting, and of course that's the setting that you'll use to test all kinds of semiconductors. FYI, in a properly designed, this is just interesting and you don't have to know it. In a properly designed meter, the difference between the diode test and the resistance test is that the resistance test will generally not put out enough voltage to turn on a PN junction. The voltage coming out of the probes that you're using to measure the resistance is less than 0.6. It might be like 0.2 of a volt or 0.3 or something. So it successfully ignores the semiconductors in an attempt to really show you as accurate of an in-circuit resistance test as you can. As I mentioned before, though, in-circuit things very often do not test properly at all. And you'll pull lots of stuff out of circuit to test it, only to test it out of circuit and say, no, definitely good. So that's just the way it goes. All right, so let's do the test with the. Oh, and I'm sorry. And then on the diode test setting, it does put out 0.6 of a volt or more really to make sure it turns on PN junction. I think it puts out a couple of volts because it turned, if you remember from the first day of class, when you lit up the LED with your meter, you got a reading of like 1.7 volts. That's the junction drop, approximately, of that LED, 1.7 volts. So we know it puts out at least 1.7 volts. The LEDs have a different junction drop because they have different, what we call dopants. I mentioned to you yesterday, and I told you didn't have to know, that we use these two dopants called boron and phosphorus for the bipolar junction transistor. The LED uses gallium and arsenic. They're called gallium arsenide. It still makes a PN junction. It just takes more voltage off. Anyway, all right. So let's start off with meter set on diode test. Put your red meter lead on the gate, the far left-hand leg. Put your black meter lead on the source, the far right-hand leg. What reading do you get? Open, right? The OL, the overload readings, open. Leave the red lead where it is. Move the black lead to the center leg, which is the drain, or, oh, you don't have a metal tap. So center leg, which is the drain. And again, you can bend the leads out if you want. What's your reading? Open. Also open, isn't it? Now reverse your leads. Remember we did this before. And this time you're going to put the black lead on the gate and check from the gate to the source with the black lead on the gate and red lead on the source. What do you get? No, it's still open. Leave the black lead where it is. Move the red lead to the drain, which is the center leg. And what do you get? Open. Open. Put the red meter lead on the drain now, which is the center leg, and the black meter lead on the source. What do you get?
5.5.
1.4.
0.4?
1.14.
Aren't you getting like 0.4, 0.5, 0.6?
Okay.
What are you getting, Chris?
5.5.
Okay. Geez, somebody that speaks English. I hear them beeping, so I know you're getting continuity there. Now reverse your leads on the same 2 points.
6.8.
Reverse your leads between the drain and source.
Yeah, open.
You get open one way, right? If you're having trouble, let's repeat that. I don't care where you start. You're checking between the drain and the source. Check one way, you'll get a junction drop, and the other way, you'll get an open reading. In other words, the only junction drop that you see is between the drain and the source. You are not looking at the MOSFET. The MOSFET itself is invisible. It's completely invisible to the meter. What you're really looking at is an internal diode. Inside the MOSFET, on the same little chip of silicon that is. Guys, gentlemen.
We get different readings. We get different readings from.
You have a legitimate concern then, I suppose. Damn your eyes. Well, that's not the device. That's not the device, isn't it?
It is.
Oh, okay. Sorry. Some have metal taps.
Yeah. So I'm trying to.
Yeah.
Now it's doing nothing. It was beeping a while ago.
Maybe you were hearing something. There you go.
There you go. Oh, now it's okay. That's the switch. My meter is very.
You interrupted me right in the middle of my dramatic reveal. So, okay, stop with the peeping. Stop. Hey, I'm going to tell your mother who's peeping. Stop. Pascal, it's you. Jeez. All right, so here's the deal. The MOSFET itself is invisible. Properly working MOSFET shows open all around. What you're really seeing there is an internal diode. Inside the MOSFET, again, on that same little tiny chip of silicon, they build the MOSFET, but at the same time they build this protection diode. It's called a protection diode. And it's really important when the MOSFET is going to be used to drive a coil of wire, as it is in a pinball machine or in a monitor, as you're going to see, or a power supply. You'll see this later on, don't worry about it. you will see that the drain itself is connected to a coil of wire. When you energize a coil, it builds up a big giant magnetic field. When you turn the MOSFET off, that magnetic field quickly collapses and it turns the coil into a generator. It makes this voltage want to rise to a very high spike that will blow out the MOSFET instantly if it wasn't protected. So there's a diode between the drain and the source. It's called a protection diode. Well, the reason why I said that you'll never have to do this whole test again is, what's the point? You're not testing the MOSFET. When a MOSFET fails, it inevitably shorts between drain and source. From the center leg to the right-hand leg will be a dead short. I've never seen a bad MOSFET that didn't do that. No technician that I talk to every real technician that I work with. Hey, have you ever seen a MOSFET do something other than a drain to source short? Oh no, they always do that. So I just want to show you something real quick here. So this is the heat sink from there's a heat sink from a power supply. It's just the heat sink with the devices attached to it. And it has a couple of MOSFETs right here. So here's one of them. You can see the International Rectifier logo. Part numbers vary from a MOSFET to MOSFET. International rectifiers are IRF, International Rectifier FET is really what that stands for. Anyway, if you look at the one on the left, it looks pretty normal, TO220 package. Look at the one on the right, and you can see it's blowed up. It's blowed up, man. It's blown up. And if you look where the crater is in this thing, it cratered between the center leg and the right-hand leg. That's where the channel is, between the center and the right-hand leg. And it just blew up. And that is not uncommon. It is really, I don't expect it to be like this all the time. It's not. But if you see a blown up MOSFET, don't go, oh my God, it's blown up, how unusual. It's not unusual at all. So bad MOSFETs fail, and when they fail, they always short at least drain to source. It is certainly possible even that all three legs will be shorted together. So the test that I use is to see if they're good or bad. You can do quickly, almost always in circuit. All you really have to do is check between the metal tab, if it has a metal tab, and the right-hand leg, or between the center leg and the right-hand leg. I just put my meter on diode test, check between the center leg and the right-hand leg. If it's not shorted, meaning it will either be open or junction drop or something else other than a short, it's good. If you touch those two, it goes beep. It's definitely bad. I have a vintage solar system at home, and it uses what's called a string inverter. Modern solar panels have little inverters on them, and you just gang them all together. But this one makes like 600 volts DC and runs 600 volts DC down into this big giant inverter, heavy thing that's hanging on the wall there. Anyway, it recently failed, and I opened it up, and the MOSFETs are just shorted. But it took me 30 seconds to diagnose it because I can see that it's a MOSFET. It's attached to a heat sink, and there's a whole bunch of them there. And I just go down the line, beep, oh, no, beep. They're just all shorted. It's kind of a involved repair. You don't really care about that. But I'm saying that you don't have to do the whole transistor test. You can do it this way, and of course now you also have the component tester that you just built that also tests MOSFET. Make sense? So MOSFET part numbering, you will probably have to Google the part number to find out what its specifications are. But let's take a look at MOSFET specs. Remember, every time we see a new part, we're going to look at its specifications. So let's look at MOSFET specs. And they're rated basically like diodes are. They're really rated by voltage and current. So the voltage rating is just like the voltage rating of a diode. It's its maximum voltage that it can handle. I think it's, I never even thought about it before. I think it's called V sub ds, the maximum voltage between drain and source. Oh, I could be wrong about that. I never even thought to look it up. I don't really care. It's just the voltage rating of the MOSFET, really. And because it's a maximum, it's the maximum that the MOSFET can handle. It is okay to use one of a higher voltage. It is perfectly okay to use a MOSFET of a higher voltage rating. It just means it can handle a higher voltage, which isn't there anyway. So, current, same thing. The current rating is the maximum current that the MOSFET can handle. And again, as with the diode, it is perfectly okay to use one of a higher current rating as well. The cool thing about MOSFETs, not the ones that you have in front of you, but some other ones, is a part numbering system that they use. International Rectifier has their own system. And if you have an IRF 530, you have to look it up. And you just Google IRF 530 data sheet, you'll get the data sheet. But some MOSFETs, you can tell from the part number, its specifications. For example, you might have something like an 8N60. That would be an 8 amps, an N channel FET, and 600 volts DC volts. You might have a 10P80, 10 amps P channel FET, 800 volts. You could have a 24N40, 24 amps N channel FET, 40 amps. So if, for example, I had, let's say this. If I had an 8N60 that was bad, and I looked through all my stuff, and I don't have an 8N60. Oh, but I do have a 10N. You cannot change the polarity, obviously. I have a 10N80. Would that work as a substitution? Sure it would. You can be higher in voltage or current or both, and you're fine. You just can't go down. I mean, that would be dumb. I give a lot of lectures on Indian reservations. In the United States, I work in the casino industry as well. Same exact technical stuff, except I don't cover CRT repair. I cover LCD repair. So I'm way out in the middle of nowhere a lot. Like really, the Indian reservations, some of them are really just out in the boondocks. And one day, one of the guys in my class brought me a brick power supply, just a regular one like that, and said, "Hey, Randy, can we fix this?" And I said, "Well, I don't know what's wrong with it. What is it? What's wrong with it?" He said, "It's the charging unit for the lady in finance or bookkeeping or something. It's a charging unit for her electric wheelchair. Her battery is dead. We don't have any way to charge her up, and she's screwed now because she's stuck. She's stuck in this chair, and we gotta get her out. And can we fix the thing?" And I said, "Well, I don't know. Let's figure out how to open it up." Or bashed it with a hammer, got the thing open. And they tested the transistors. They found a bad MOSFET, shorted MOSFET. I can't remember the number. I'll pretend it's a 4N40 or something. So I looked through all my Jazzola, and I didn't have that one. I had some parts that I had with me, but I found one that was way higher in current, way higher in voltage. Use it, stick it in, worked perfectly, got everything charged up. It works fine. So as a technician, that makes me feel real good. I love to be able to do that kind of stuff. It's most electronic repair is simple. Once you know what you're looking for, I think anybody can do it. In repair, you're not designing something. Everything you work on used to work at one point. So at this point in the class, you already know how to fix stuff. You really do. I mean, how do you fix stuff? You look at it, you see some parts, you go, oh, I know what that part is. You test the parts to see if they're good or bad. So for the rest of the class, we're really going to look at the actual circuits themselves and how they all work and that. And it's going to get complex. As I said, every day it's going to get more and more complex. And today is going to be real complex. But I really kind of want you to relax, pay attention because you're here, but relax because you already know how to fix stuff. You already know how to test components, and you already know how to solder like crazy. And what else is there? I mean, not much except how the things work and being able to get to the problem more quickly now. So that's what we're going to work on. So I think it's about break time, isn't it? So let's take a break. Yeah, close enough.
Yeah.
It was the first day that
Yes, sir.
right. So now
Oh, wait a minute. That may happen. Some MOSFETs are very sensitive, gate field sensitive. If you somehow accidentally gate it, I'm not sure how you do it, but you short these two together. And do me a favor, put your button and leave it on there. And then that's just leave it on. That's just really there. Let me see if I can just turn it on by doing that. See, and now you see a reading because I accidentally shorted the gate to the drain first, and then I turned it on, and it keeps it turned on. It doesn't take very much energy to turn on. You did it with the meter. Static? No. These are. This is way improved. The original MOSFET, the original FETs were very static, but MOSFETs are rugged. No, you don't have this whole thing. That having been said, would I really rub my feet on the carpet and hit it? No, I wouldn't. Yeah, no, I wouldn't. But it is not inherently susceptible to static.
Hij is nu continu bezig, hij is tijdrekken.
Kan je dat op een video kijken? Kan je dat op video kijken? Nee, dat komt wel van de camera. Kan je dat op een video kijken?
Als het is wel, maar
Van de theorie kan je met kleine
ik kan streamen, ja. Ik kan gewoon
een
video's
livestream doen en erin kan.
Ja, maar het is heel groot. Het is niet zo'n video.
Dat is niet belangrijk.
Ja, maar
Ja, hij kan een 360 graden opnemen bij 1 pixel. Ja.
1 bij 1 pixel.
Je kijkt gewoon een beetje wat de ambient lighting is.
Het is wel uit. Je kan een 8K video hebben en als het nog zwart is het nog steeds 1 pixel. Het gaat om hoeveel complexe dingen in doen.
Je kan heel efficiënt zien als het maar in een compleet donkere kamer is.
Ja, dat is wel waar. Dat was een bedrijf dat deed webcamlijst. En die hadden een heel mooi huis gemaakt waar die allemaal in moesten zitten. En het eerste wat ik zag was dat ze een fancy patroon op het behang hadden. Ik had gezegd van, dat weg jongens, dat ga je zien beste. En ik had absoluut gelijk, dat heb ik niet gedaan. Dit is groter. Het ding wat je ziet met het maakt, is moeilijk af.
hij moet weer uitslopen. Shit. Moet dat gezegd worden, gezien. Top. Kun je zien wie er kijken?
Dan. Die
Oh,
kopjes rechtsboven de chat.
Dat is alleen die ingelogd is.
dan kijken ook mensen die niet ingelogd zijn.
Ja, ik ben nooit ingelogd.
Ja.
Je kan alleen niet zien welke van die mensen bots zijn.
Oh. Dit is toch wel een lijstje. Ja. Zijn die vakjes allemaal net zo beneden? Nee, ik heb het heel veel gedeeld.
Is dat niet echt aangezet? Dat is wel.
Ik heb het in de Aussie-archief gezet.
Ah, oké.
Daar zit het op die koude bijvoorbeeld. Zien en koude voor. Dus die hebben een cursus met een foto. Ik dacht, nee, dat staat daar komt in. Je kunt ook kijken wat voor je.
you awake?
More or less.
Sort of. Okay, so now and for the rest of the day, we'll be talking about power supplies. Be aware that as I start discussing power supplies, I'm really talking about starting on CRT monitors. We have lots and lots and lots of power supply failure in monitors. Lots of them. There's lots of power supply failures in everything. Power supplies are the #1 failure, like worldwide, I guess. Really, power supplies fail. They're working pretty hard, and they just fail. Like the last couple of computers I had to, honestly, I replaced the power supplies a couple of times. Even though I know what's wrong with the power supply, honestly, in a modern switching power supply for a computer, by the time I take it all apart, fix the darn thing, I might as well spend $60 on a new power supply. I just don't think it's practical. And in your situation, in a game of collector situation, obviously you have to fix the thing. But in the modern world, I don't know. I mentioned to you that I'm also in the casino business. In the casino, power supplies are unbelievably expensive. A slot machine power supply can cost $500. So you really have to be able to fix those things. You can't really afford to throw them away. So as I start talking about power supplies, I'm really starting on CRT monitors, which will be the full day of that tomorrow. Right? So there are two different kinds of power supplies that exist. One type, the first type I'm going to talk about, is technically known as a linear power supply. It's called a linear power supply. For reasons that I may or may not really discuss, it has to do with the operating curve of a transistor, which is probably something you don't need to know. A linear power supply is also known as a conventional power supply. A conventional, again, meaning just ordinary. When we use the term conventional electronics, we mean there's nothing special about it. It's the same kind of power supply that we've been using for 100 years, same exact design, different actual hardware, but the same design, does the same thing for probably over 100 years, really. Conventional power supply, also known as a linear power supply, and this is what's in all of the classic arcade games, the games with the power supply audio regulator board, or whatever they have. The onboard power supply on a Pac-Man is a linear power supply. It's just everything from that era, because they had not invented the other kind of power supply, the kind of power supply that's in modern things and in more modern monitors, everything after about 90, maybe 90. This kind of power supply, which we'll talk about next, and that kind of a power supply is known as a switching power supply. T-C-H-I-N-G. It's called a switching power supply, or more correctly, it's really called a switching regulator. Switching regulator power supply. This kind of power supply is also referred to as a switched mode power supply. It's called a switched mode power supply, or SMPS, as it's called in the monitor itself. Typically in the monitor, we refer to the more modern power supply in a monitor as the SMPS, the switched mode power supply. What's interesting about that is, like, virtually the same design when used in a low voltage power supply, we refer to as a switching regulator power supply, like the power supply that's in your computer, and switching regulator power supplies. But like virtually the same design when used as part of a monitor, it's referred to as a switched mode power supply. I go figure. electronics. You know, electronics is kind of crazy. So we're going to start with a linear power supply first because it's important for you especially to understand how the linear power supply works, because lots of monitor failures are power supply failures. We're going to go over that in a lot of detail, and then we're going to cover switching regulator power supplies, which are much more complex. How they work is way more complex than the linear power supply, but are in fact easy to fix. Really easy to fix. You'll see how this works. So what the heck is a power supply? Turn in your book to some sort of page here. Hang on. 95 maybe? For you listening at home, you may purchase a copy of the textbook online. So this here page. So what the heck is a power supply? I mean, obviously the power for the game comes from the mains. That's where it's plugged in. That's its power source. But remember, we talked about this previously, that is alternating current. It's AC, it's alternating current. Alternating current, as I mentioned previously, is really good for motors and toasters and things like that. And it's also fantastic for power transmission long distances. AC is really great for that, but AC is not good for electronic stuff. All electronic stuff really, has to have DC to operate. So what the power supply is doing is taking in alternating current and giving us out direct current. Now at the same time, it really likely changes the voltage as well. It's not a requirement to call it a power supply, but it likely does. So a low voltage power supply might take in the mains voltage, 240 volts AC here, 120 volts AC in North America, and give it a bunch of outputs. It might just be a 12 volt output. It might include also, or it might be only the 5 volt DC output. The 5 volt DC output, and we'll talk about this, of course, later on, that has to be really accurate, and it can only vary plus or minus a quarter of a volt, really accurate. I mentioned to you I'm in the casino business. Lots of those power supplies have 24 volts DC, 24 volt output. And there's lots of other things. Your computer at home requires a 3.3 volt DC output that powers the microprocessor itself. And there might even be plus like 1.7 volt DC power supply that powers a microprocessor. So there's lots of different voltages. So it might have low voltage output. It might raise the voltage. We don't really use it in the amusement business, but it's very logical to have a power supply with 240 volts DC in and 1200 volts DC out. I don't know what the heck you use it for. Something. It could be anything. It really is. So in that case, it raises the voltage. But that's not a requirement. We have one monitor. You're probably familiar with the Electro Home monitor from last century, like Stone Age monitor. And in the United States, in the game itself, it gets 120 volts AC input, but the DC power supply output is 120 volts DC. So in that case, it doesn't change the voltage at all. It just changes it from AC to DC. So regardless of whether it changes the voltage or raises it or lowers it or keeps it the same, the power supply is changing alternating current into direct current. Everybody would be on the concept there, right? So before we get going, let's take a look at alternating current. And what's shown here is just a simple graph. This is the same graph that an oscilloscope draws, as you probably know. An oscilloscope is just a graph drawing machine. It's got a little screen on it. It's got like 8,000 knobs, and you got to be like really a bitch of genius to be able to use it. Yeah, don't get me wrong. I have a couple scopes. I love oscilloscopes. I have almost no reason to ever use it though. Like I said, I fix everything really in the monitor with a regular digital multimeter, an ESR meter, and that's really it. It's fun to use a scope, but it's not necessary. Anyway, all a scope does is draw a graph like this, and it's a simple graph that shows time in the horizontal direction versus voltage in the vertical direction. So this is what alternating current looks like everywhere in the world. This is what comes out of the receptacle everywhere in the world. This is what comes from spinning a coil of wire inside a magnetic field. There's a couple of ways you can generate electricity. One is, like you guys do here with the big turbines, you're taking a coil of wire and spinning it inside a magnetic field, and that's what makes a generator. The other way is that you can have a stationary coil and spin the magnetic field around it. From terms of physics, it doesn't know the difference. It doesn't matter what's going on, whether the magnetic field is stationary or the coil's moving or the magnetic field is moving. It doesn't make any difference. It still turns it into a generator, and that's what comes out. Different frequencies, different voltages. Like Japan, it's 100 volts and 50 hertz, and like I mentioned in USA and Caribbean and like that, it's 120 volts and 60 hertz. All right, so there's a line down the middle labeled 0 volts. That's ground. Ground, as you know, is our 0 volt reference. Well, alternating current is always changing direction. For a while, it goes this way. Let's call it positive. Then it stops and it turns around and goes back the other way. And here it does that 50 times a second. So where the current is positive, I'm going to draw a line above ground, and where it's negative, I'll draw a line below ground. Simple graph, right? So nothing's instantaneous. It takes a certain amount of time for things to happen. So as the coil spins in the magnetic field, or vice versa, the voltage begins to rise over time. And as it rises, it's the voltage rising. In other words, here's plus 10 volts, plus 20 volts, 30, 40, 50, whatever it is, until it reaches what we refer to as a peak, depending on the voltage, how tall the peak is. But it's only at the peak for an instant in time. It is a point on a line. It has 0 duration. It gets to the peak and immediately drops back down. So this is the positive half cycle. It rises until it reaches whatever the peak is, and then drops back down to 0 volts. We refer to that as zero crossing. This is known as zero crossing. Zero crossing can be really important in some situations. When you're energizing a load, like turning on a pinball coil, you don't want to turn on the coil when the voltage is at its peak. If you can turn on the coil when the voltage is at 0, you don't damage anything, and then let the voltage slowly ramp up. You don't really care about that now. We'll talk about that in a little bit of zero crossing. But then it keeps going down in the negative direction. This is the positive half cycle. Now we're going negative. In other words, this is maybe minus 10 volts, minus 20 volts, and so on, until it reaches a negative peak that's just as far below ground as the positive peak is above ground. But again, it's just there for an instant in time, and then it comes right back up, and that is the negative half cycle of the alternating current, and that is one cycle. So here we're talking about 1/50th of a second. That's a 100th of a second, 100th of a second. Here we go. And then the process is repeated 60 times a second. So just to change the scale of this thing here, let me just change the scale of it. We end up with this. that, right? The positive, negative, positive, negative, positive, negative, and so on, like this. And so this picture that I've drawn here has a name. It's called a waveform. W-A-V-E-F-O-R-M. It's called a waveform. This particular waveform has a name. It's called a sine wave. S-I-N-E-W-A-V-E. A sine wave. And I've seen it written as one word and two words. I'm not sure if it's sine wave or sine wave. I've seen it like both ways. I don't think it makes any difference. But again, this is what comes out of a coil of wire when you spin it in a magnetic field. So there's the positive half cycles and there's the negative half cycles. So that's what comes out of the wall receptacle.
So then is the highest point to the lowest point? Is that 100 volts or how?
Oh, we're going to talk about that specifically.
Yeah.
We're absolutely. It's a great question. I will answer that question coming up. So it's an excellent. It's an excellent question. It's just an excellent, super excellent. All right. It's the most wonderful question. So anyway, so that's what AC looks like. If I were to draw a graph of direct current, what do you suppose that would look like? Anybody? Yeah.
Just a straight line across where.
Sure. It would just be a straight line, wouldn't it? Well, why? Well, let's think about it. Here's ground. Here's our 0 volts. If let's say it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 volts here. So if I have a battery and I measure the voltage here, it's 9 volts. If I measure the voltage now, it's 9 volts. Remember, it's time in the horizontal direction. Measure the voltage now, it's 9 volts. I measure the voltage tomorrow, it's 9 volts. Whenever I measure it, it's 9 volts. So that's why on your meter, remember, volts DC is indicated with the dashed line, which indicates ground, and the straight line above it, because that's what it looks like, and volts AC shows you what I can now refer to as the sine wave, as opposed to just a little squiggle. It's the sine wave, so that means AC. So somehow the power supply, however it's doing it, it's changing that into that. Is everybody with me on the concept? Essentially, what a power supply is doing is simulating the DC output of a battery. And in fact, when they first made power supplies, they weren't called power supplies. They were referred to as battery eliminators. Like way back when radios had valves in them. For you in the UK, they're called valves, vacuum tubes. In them, they were battery operated, but vacuum tubes draw a tremendous amount of power. I mean, they have a little filament inside. We'll talk about that tomorrow. A heater inside, and they're real hot, and they just waste a lot of power. So listening to the radio back then was a big deal, as you know. It was like, a program's going to be on. Everybody gather around the radio, and you turn it on a minute before the radio program came on to let it warm up, and you listen to your radio, and then turn it off right away. So they made these what they call battery eliminators, but now we call them power supplies. So anyway, so if you turn in your book to the previous article on transformers, page 91, please. It's really neat that Hassan printed these books out in color. I don't. I print them in black and white. In black, I guess. Okay, so remember, we're talking about the linear power supply first. We're going to talk about the linear power supply first. And in a linear power supply, if the power supply is going to change the voltage, which it really probably will, it does that first. First, it changes the voltage, then it's going to change it from AC into DC. And it does it with this here part called a transformer. So conceptually, what a transformer is two coils of wire that are wrapped around the same magnetic core. Two completely separate, isolated coils of wire, but they're both wrapped around the same iron core. This iron core is made out of laminated iron pieces. You don't really have to know this. It's not like a failure item or anything, but it's made of iron laminates called E's and C's. Some are shaped like this. Some are shaped like this. Just really, like, you can really clearly see it. They're flat pieces of iron all kind of stacked together. And in the middle, there's a core that goes down the middle. I'll draw it on the board in just a second. In this case, you can clearly see the two coils of wire. There's a coil of wire here on the top and a coil of wire here on the bottom. These are referred to as the bobbins, like sewing bobbin, B-O-B-B-I-N, a bobbin. Again, you don't really have to know that. Right? That's just how it's made. So there are two completely separate coils of wire, one stacked on top of the other. There are two ways that transformers can be built. They can be built like this with one coil stacked on top of the other, or that may be one coil stacked, wound on top of the other like this. They both work the same way, whether it's two different coils like this, or one inside and one outside. They work exactly the same way, two different ways to do the same thing. It is two coils that are sharing a magnetic field. So what it looks like, or how it's built, is like this. Like this. So there are two coils of wire. Oh, and it's made of these laminates. Yeah, again, it's made out of these iron laminates. If it was made out of solid iron, it would heat up. There's a thing called eddy. You don't have to know this. Eddy currents, the magnetic currents within the magnetic core, and this prevents that from happening. It would get like super hot. Yes.
I think you have to press the button once.
Oh. Well, that's okay. I'm just on the board. I wonder why it times out like that. It seems silly.
I think it's like timeout or something, maybe.
What? Yeah. I mean, it clearly is timing out. All right. So there are two coils of wire that share this core. So one coil of wire is wrapped around the core like this. Many more turns of wire than I've shown you here, like a lot of turns of wire. And it's insulated wire. Not insulated wire like they used in the first kit, but it's varnished wire. It's not like thick plastic insulation. It is copper wire that is varnished with a varnish, which insulates it. And then there's another coil of wire wrapped around like this. So two coils of wire that share the same magnetic core. I mean, that's how it's built. The schematic diagram looks like this. There's a coil of wire here on the left. Two vertical lines that represent the core. Two vertical lines that represent the flat pieces of iron that are all stacked together. And another coil of wire here on the right. They are two completely separated coils of wire. The one coil is completely isolated. We'll talk a lot about this in a second here. The two coils are completely isolated from one another. In other words, there's no electrical connection between the two. It's technically called a galvanic connection. You don't have to know that. Named after Mr. Galvan. They're not, there's a million, billion, zillion ohms between them. They're isolated from one another. Anyway, so the coil on the left has a name. It's called the primary. It's called the primary winding of the transformer. And the primary winding is the input side of the transformer. The coil of wire on the right is referred to as the secondary. It's called the secondary, or the secondary winding, really. And that's the output. And this is true of schematic diagrams in general, by the way. it's really helpful to be able to read schematic diagrams, and in a properly drawn schematic diagram, inputs are on the left-hand side and outputs are on the right-hand side. So, for example, as we're looking at monitor schematics later on, what is an input to the monitor? Well, the input into the monitor is the red, green, and blue signals, as you probably know, that come from the board itself, and a couple of synchronization signals. Just relax, we'll talk about all that. But that's the inputs. If I was looking at the schematic diagram of a monitor, I would look on the left-hand side for the inputs. That's where they go. That's where they'll be. On the other hand, the monitor has one output. What is it? It's the picture tube, the CRT itself, the screen. This is the one and only output. It doesn't make any noise, so that's its only output. And that, of course, is on the right-hand side of the schematic. Any monitor schematic that you've looked at, and you've got a bunch of them in that the big book, it's on the right-hand side. So inputs are on the left, outputs are on the right. And as we look at the circuit, the signals, the actual thing that you're doing with the electricity, moves from left to right. So since the primary winding is the input, let's hook it up to the mains. It's the input, so here we go. So this is how I draw the mains anyway. That's what our silly little plug looks like in the United States. I guess I could make them round somehow. Anyway, so there's the mains. The primary winding will always be connected through a fuse. The primary fuse, F1 in this case. I can't imagine why it wouldn't be F1 anyway. And the two vertical lines that represent the core, and then over here is the output. Well, remember I started this discussion by saying, hey, in the linear power supply, if it's going to change the voltage, it does that first, and it does it with the transformer. And the way it does it is by virtue of what's known as the turns ratio of the transformer. The turns ratio. Just relax. Here's what I mean by this. Here's what is meant by this. Over here on the primary winding might have, let's say, just for the sake of discussion, 1,000 turns of wire. That's a turn is a wrap. One wrap around the core. 1, 2, 3, 1,000. And for the sake of discussion, let's say that the output over here had just 100 turns of wire. Question, not a trick question. What is the turns ratio? Not a trick question.
Sorry, 10 to 1.
What is it? It's 10 to 1, isn't it? There's 10 over here for every 1 over here. So the turns ratio is 10 to 1. Well, in the transformer, the turns ratio equals the voltage ratio. That's how they make the thing. That's how they figure out how to make it. The turns ratio equals the voltage ratio. So in this case, if I put in, let's just use my USA number for the sake of discussion, since I'm more familiar with using it. Let's say we put in 120 volts AC, which is the input on lots of the games there. What would the output voltage be? 12 volts. And it's 12 volts AC. This is super important. The output of a transformer is strictly AC. A transformer doesn't really have anything to do with DC whatsoever. The way a transformer works is that, remember we're putting AC into this thing. And remember what alternating current looks like. It looks like this. So right here, the AC is 0 volts. Nothing's happening. As the voltage rises, current starts to flow through the transformer, and it builds up a magnetic field. The higher the voltage, the bigger the magnetic field is. But because they're both wrapped around the same magnetic core, even though they don't touch each other, that magnetic field surrounds the secondary winding as well. And as the magnetic field builds up higher and higher, it forces electric current out the wire. You can kind of think of a copper wire as like a garden hose. It's already full of water. Instead of water molecules, it's full of electrons. And electrons are pushed around by a magnetic field. So as the magnetic field builds up, there's this tsunami of magnetism. It forces electric current out the secondary, even though they're not touching each other. So then the voltage drops down to 0. Remember, that's called zero crossing. The magnetic field collapses. So it builds up and collapses. But now the current's flowing in the opposite direction. It was the positive way. Now it's negative. So now the magnetic field builds up, but with the opposite polarity. In other words, where first it was, let's say, north pole up here and south pole down here, that collapses at zero crossing. Then this is the south pole, this is the north pole. So it builds up and collapses, builds up and collapses. And as it does that, it shoots the current out the secondary winding. Again, even though the two are isolated from one another, there's no direct electrical connection, we get AC to come out the secondary. But it's real important to remember this. The output of a transformer is strictly AC. AC, AC. Transformer output is AC, AC, AC. Now, the input is also AC in this case. The input doesn't specifically have to change polarity for the transformer to work, but it does have to move. This will come into play when we start looking at the switching power supply later on today. So as long as the magnetic field moves across the coils of wire in the transformer, we will get an alternating current output of the transformer. It does not specifically have to change polarity, north pole, south pole, north pole, but it does have to move, build up, and collapse. So that's how we get an output from the transformer, and the output voltage depends on the number of turns, the windings. How many actual turns does the thing have? Does it have? And that's how the manufacturer determines how to build the thing. We don't care about the number of turns. The thing comes to us already built. We only care about what the voltage is. But I mean, that's how the guy figured out how to do it. I went to Taiwan, and I had a chance to visit my friend Peter Chow in Taiwan. How many of you have seen the Peter Chow power supply? Worked on Peter Chow. So he's a real guy, and I went to visit him in Taiwan, and I went to his factory, and it was real interesting. And I saw kind of a manufacturing district in Taiwan, and I always imagined in my mind like a manufacturing plant in China, Taiwan, like a white room like this with long tables, ladies in hairnets, and like that. It's not. It's one Chinese guy in his underwear smoking cigarettes on a winding machine, and he has like a foot pedal and a winding counter. And he puts the bobbin on there, winds it, and takes the bobbin off, and that's what it is. In a dirty old little garage making transformers. This is his whole life. So it was kind of weird. It was neat meeting Peter, though. He's a cool dude. He's a very, very interesting fellow. I got some stories, but I won't tell. Anyway, a transformer like this that takes in a higher voltage, again, in this case 120 volts AC, and lowers it, is referred to as a step-down transformer. This is called a step-down transformer for obvious reasons, because it steps the voltage down. You may see transformer, by the way, abbreviated XFMR. For some reason, X means trans. I don't know why. In the world of electronics, it means trans. Like, for example, you'll see transistors abbreviated XSTR. We'll see this tomorrow when we start looking at the electrohome monitor schematic there. The transistors are like X101, X903, X this, which is kind of weird. So anyway, this is called a step-down transformer for obvious reasons. You can have a step-up transformer. They make step-up transformers.
Randy,
yes.
Why is it important for an arcade? I've seen you say in your video that, in particular, Mexico, I would say that more than 50% of the machines don't have a transformer. They removed it at some point, or they rewired it for not to use it.
They don't have an isolation transformer. Yeah, we'll talk about this. I'm getting there. I'll answer your question. Both questions. I'll answer your question. Just comment these. It's okay. I'll answer your question. So it is possible to have a step-up transformer. A step-up transformer has more turns of wire on the secondary than the primary. The more turns of wire you have, the higher the voltage will be. So it's possible to have a step-up transformer. We use them in the monitors. As you know, there's a super-duper step-up transformer called the flyback transformer that takes in 120 volts or 130 volts and turns it into 36,000. So that really steps up. We'll talk about that guy later on.
Does that mean that if you flip the transformer around and you put 12 volts on one side, you get 120 on the other side?
Yes, correct. If I had a transformer that was a 12 volt AC transformer, and I put 12 volts AC into the secondary winding, I would get 120 volts AC out the primary. And in fact, when I was a kid in high school, we built an inverter that did just that. We built our own little 110 volt inverter, and it used like a TIP 31 or something like that, and gave it 12 volts, and we got 120 volts out. Now, it is possible to have a so everybody wake up. It is possible to have a transformer with a 1-to-1 turns ratio, and it's called an isolation transformer. It's called an isolation transformer. Transformer with a 1-to-1 turns ratio. Whatever you put in, you get out. If I put in 120 volts AC, I get out 120 volts AC. If I put in 240 volts AC, I get out 240 volts AC. Seems like a useless piece of junk, doesn't it? But it's a kind of a safety transformer. Many of the older monitors, all of the older monitors that we use, not this one, are what are referred to as hot chassis monitors. It's one of the first things we're going to discuss when we get into monitors. The monitor itself, the metal chassis, is connected to the mains through a diode. There's one diode that connects between the mains and the chassis, and it makes the chassis hot to, in America, ground. It's a difference in how your power systems work, and we're going to talk about this a little later on. What the isolation transformer does is breaks the ground connection. I'll explain it in terms of USA, because the games are built in USA, and you're wondering how you get away with no transformer, and sometimes you do, and sometimes you don't need one. In the United States of America, the way our power works in North America is the AC power, you have what we refer to as the hot side. Sorry, let me do it this way. In America, our AC power system looks like this. There's a short slot, there's a wider slot. It is polarized. The short slot is what we refer to as the hot side of the AC power. We happen to use a black wire for it. You don't really, I suppose, have to know that, but it's a black wire. It is the only wire that has juice on it. The other side over here, the long lead, is called neutral. Theoretically, I can stick my tongue in that slot and not get a shock. But this is the one that has the power on it. And then we also have this kind of a half round slot here, and that's ground. That is our earth ground. We call it ground. You guys call it earth. And in fact, you call it earth, right? You have a earth, which is like a common 0 volt connection. But then earth is specifically connected to the earth itself. It's a water pipe that's buried in the ground, or a stake or a rod in the ground. It is connected to the earth itself. And it's sort of it's a safety ground. In the United States of America, these two wires go to the inside of whatever equipment it is. The earth ground is connected to the outside of something. By law in America, every single bolt head, every single thing that's metal, that's touchable by a consumer, has to be grounded to an earth ground. And in fact, I prepared a bunch of games to go to Russia for export, and I was so surprised. Russia, to import our games, required retrofitting some of our oldest stuff with earth grounds where people had done conversions and left off the grounds. We had to make sure that everything was grounded, or it wouldn't pass inspection for import. kind of weird. So there is another kind of a transformer that exists. We'll get back to the isolation transformer in just a second. There's another kind of transformer that exists that has a primary winding, and when they're winding the secondary winding, they stop exactly in the middle and pull out what's known as a tap. And then they keep winding. The Chinese guy stops the winding machine, reaches in there, grabs a wire, pulls it out, and takes a break, and then rewinds the rest of the coil. So there's just as many windings from the tap to one side as the tap to the other. It's right in the center. It's called the center tap, right? So the way our AC, we'll look at that some more in just a second. The way our AC power works in the United States is that the center tap is the neutral. We have 120 volts AC that goes to our homes, where you guys have 240, ours is 120 going to the actual house. But we have two, what we call phases. There are two phases here. There's between the neutral and this side, and between neutral and the other side. Remember, it's the number of turns that determine the voltage. If I have the same number of turns from one side to the other, it's going to be the same output voltage. And in the United States, at the circuit breaker panel, neutral and ground are connected together. So they're really one and the same, but when they're hooked up, ground goes to the outside of something and neutral goes to the inside. Therefore, we have to break, in the United States of America, we have to break this neutral ground connection, or something terrible will happen. When we start looking at the power supply, you'll see why. Something terrible will happen if we put a safety ground, an earth ground, on the hot chassis. We are now putting a diode right across the AC power, and it destroys the diode. It vaporizes traces off the board, things catch fire. It's a super bad deal. So what the isolation transformer does, and remember that's our real discussion here, isolation transformer, is that it breaks the neutral ground connection. Over here we have a hot side and we have a neutral side. This side, the neutral, is connected to the earth ground. But over here, this output is what we call floating. It's floating. The output here is floating. In other words, it's not connected to anything else. It's not referenced to anything else. It's like a battery, only it's AC, just kind of floating there. It's just not hooked up to anything else. And this is how your power system works, and sometimes yours in Mexico as well. Your power system here especially isn't like ours, where it has a grounded output. It has, I think, just the two holes like that. I think. I don't think it's connected to earth ground. Are the metal rings on the outside, are those your earth ground connections?
Yeah.
So do you happen to know? Because I really don't. In your system, it's not like this, is it? No, you don't have one side connected to ground. It's a whole separate earth ground.
Yeah.
Okay, so it is like our system, but it isn't the center tap, I guess. I'll have to look that up. I'm sorry, I just don't know that. Well, the point is this, that if the output is not referenced to ground, if your AC power is not referenced to ground, you could, I think it would be really stupid, run AC power right to the monitor itself, right from the mains connection. But what the isolation transformer does, remember almost all transformers have this property of isolation, is it breaks that neutral ground connection, so that is just floating, and it's like a safety transformer in one case, and the other case it really prevents destruction of the power supply. You'll see why in just a little bit. If for some reason the frame itself is grounded to earth ground, which it will be and it should be. And so we have to break that. So that's what the isolation transformer is. However, in more newer designs, which we will talk about as we go through the class here today, the power supply is a switch mode power supply. And in a switch mode power supply, you'll always see like a yellow transformer here. In this case, it's not an isolation transformer, but switch mode power supplies, as part of their design, as you will see today, are isolated as part of the design. It is not an isolation transformer that's hooked up to the AC power, but it does have this property known as isolation. And you can tell if this is a kind of a switch mode power supply by the transformer here. It has this yellow mylar tape on it. I don't know if it's a standard or whatever, but they're all red. I mean, all yellow. They used to be red, but they're all always yellow. So if you see that transformer, it's a different kind of power supply that does not require an isolation transformer. So they may be removing the transformer just because it's kind of a valuable thing to have a transformer, and if you don't need it, why use it? It is okay to power a monitor that has a switch mode power supply with an isolation transformer. You can have 2 transformers, that's no problem whatsoever, but you can't have none. You have to have one transformer or one kind of transformer or the other. Otherwise, depending on where you live, and Mexico's like this, you have a 50-50 chance of blowing stuff up. Depending on whether the neutral is here and the hot is here, or the neutral is here and the hot is here, one way it works perfectly, and if you flip the plug around, it blows up. I think this is probably the answer to your question. So anyway, so the one-to-one transformer is the isolation transformer, and it is not at all unusual to have multiple outputs. It is, since most systems require multiple voltages, like 5 volts and 12 volts or whatever you need, 120 volts for the monitor, it's not at all unusual to have a transformer with multiple secondaries. And in fact, it's more common really to have multiple secondaries than just one output. It's kind of silly from a manufacturing standpoint to have multiple primaries and multiple cores and multiple secondaries when I can have one primary winding, one core, and just wind as many secondary windings as I want on the thing. So, again, one might be a center tap transformer winding that turns into 5 volts, and this might be 12 volts, and this might be 24 volts. But whatever it is, it's AC coming out. The output of a transformer is AC. So that's how we change the voltage. Remember, I started off this thing by saying, hey, it's a linear power supply. If we're gonna change the voltage, we do that first, and we do that with this part called a transformer, which is insanely reliable. You probably will never ever change a conventional transformer. I have changed like 5 my whole life, 3 of which like caught fire. I mean, it's plugged right into the mains and weird things can happen, but by caught fire, I mean like smoke and stuff was pouring out of it, so obviously it was bad. The old transformers, they used to put them in a can and fill the inside with tar, pitch. And that was to keep the windings from vibrating and making noise. And when it would overheat, all the tar would run out and it would burn up. But it's not like that anymore. And I don't think you have anything weird on the floor, even in this place, or maybe your place, where you'd have a problem with the transformer failure. They're just, I'm not saying you can assume that they're always good. And we'll talk about how to troubleshoot later on. But the chances of a transformer being bad are pretty slim. Okay. So, I'm kind of a geeky guy, and I like to build stuff. And let's go back to our transformer here. And again, just referring to the United States of America, so I don't get the math wrong. I have 120 volts AC into this 10-to-1 transformer. So there it is. There's the fuse, F1. So there's the primary winding. There's the 12-volt secondary winding. And I want to do something with this. I want to build something with this transformer. So I look through my piles of junk, and I find a motor, a 12-volt motor. Okay, well, let's hook it up. And the schematic symbol for a motor is just a circle with an M in it. And, that's the actual schematic symbol for a motor. So I plug the thing in, fire it up, and it doesn't run. It doesn't turn. I can hear it kind of making a humming sound, but it isn't actually rotating. So I look at the motor more carefully and I see why. It's a DC motor, but remember the output of a transformer is AC. Thank you very much. Super important. AC, 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 right? So if we trace the current flow here, we kind of have to do it one step at a time. Remember that we have a sine wave like this, and sometimes it's positive and sometimes it's negative. So let's look at it, let's say when this side is positive and this side is negative. The current, according to the way the schematics are drawn, flows from positive to negative. So the current's going to flow this way for the positive half cycle. It's going to flow through a motor, giving it a little shove. That's our source, right? Remember, you need the four things. We have the source path, the load is the motor, and then our return path. Remember, we have to return the current back because we need two wires, right? So it gives the motor a little shove. But 1/120th of a second later, when the polarity is reversed, now this side's positive, this side's negative. Now current's going to flow in this direction and push the motor back where it came from. And in fact, the motor has so much inertia, it's not gonna move. Really, it's not gonna go because this is happening at 50 hertz, or really 100, right? Because that's a 50th of a second, so that's 100th of a second. So every 100th of a second, it's reversing polarity. It doesn't have time to get up to speed at all. It's just gonna sit there and hum and stuff like that. It's not gonna do anything at all. And of course, this is the way crane games work, is with DC motors, of course. You know, you have a motor in the crane game, and when you press the joystick forward, it goes forward, you pull it back, it just reverses the polarity on the motor. There's a circuit called an H, you don't have to know this, circuit called an H bridge. You just use it to control motors. It's pretty simple. So anyway. So this is our problem. Our problem is that the motor's just sitting there. I want to make the motor turn, and I can. I'm going to break this path, and I'm going to put a diode in here. I'm going to connect the diode in series with the motor. Remember, anytime current has to flow through one thingy to get to another thingy, they're said to be in series. So let's see what happens now. When this side is positive, and this side is negative, will current flow through the diode and get to the motor?
Yes.
How many people think yes, it will? Cool. Okay, great. So if you can look at this and say, yeah, it definitely will get to the motor, what you just did was you read the schematic. That's what reading the schematic is. Nobody can sit down with you and go, here, buddy, hey, let me show you how to read a schematic. Pull out your schematic. Read this, know what I'm saying? You know, that's just not going to happen. But once you know how the current flows in a circuit, you know how the parts work, you can read a schematic. Does it get more complicated than this? Obviously it does. But, you know, with time, you can. However, the way I teach the class and the way I fix stuff, generally speaking, you don't need a schematic diagram. Sometimes you don't get schematic diagrams. In the casino business, they're very secretive about their schematic diagrams. You have to fix their $500 power supply. Say, hey, I'm a tech. I'm working on one of your $500 power supplies. Can I have a schematic, please? Oh, no, it's proprietary. Well, I'll sign a non-disclosure agreement, whatever. It's a complicated power supply. I really need to fix it. Oh, sorry, can't help you. What? You know, so you have to be able to fix stuff without schematics. Anyway, so yes, you're right. It will go through. So the current flowing from positive to negative flows this direction. Is that the way the arrow's pointed? Yes, it is. So it flows through the diode, flows through the motor, gives it a little shove. Our return path is back to what is now the negative. 1/120th of a second later, what the current would like to do when this side's positive and this side's negative is it would like to go this way, but of course it cannot because the diode is reverse biased. Remember, when it's turned around and blocking the current flow, it is reverse biased. And if you think about it, if it's reverse biased, meaning it's not conducting, isn't that the same as if I had a big break in the wire? I mean, it's the same thing. No, nothing's getting through it. So when the current flow is reversed, nothing happens. We're not pushing the motor back. It will coast along because we gave it a pulse to kind of give it a little kick and get it going, but it's not being shoved backwards. And then 120th or 100th of a second later here, when the polarity reverses once more, follows the red path, and again, this side is positive now, this side's negative, and current flows through the diode, through the motor, gives it another little shove, and then the polarity reverses again following the blue path, and it just kind of coasts along. It's not being pushed back. So by putting one diode in there, we've made the motor turn. By putting one diode in there, we've changed the alternating current into direct current. What we did was this. Here's the sine wave. And remember, these are the positive half cycles. And these are the negative half cycles. The diode allows the positive half cycles to go through, but eliminates the negative half cycle. And this is DC. This is direct current. It's certainly not the straight line that we're looking for. We're not there yet, not by far, but, well, not far away, but we're not there yet. But it is direct current because the definition of DC is current that flows in just one direction. In this case, it's just flowing in the positive direction. So the current's flowing like this through the diode, but then it can't go back. It's flowing like this through the diode, but whoa, I can't get back. Flowing through this, and so it is DC, but it's kind of a shitty DC that we refer to as shitty DC. It's called shitty DC. No, it's not called shitty DC. No. It's called pulsating DC for obvious reasons. You've probably heard the term. It's called pulsating direct current for really obvious reasons because it comes out in pulses. But it is direct current, and we could certainly use it to drive a motor or something like that. But it's not very efficient. It's not very efficient because half the time we're just sitting there. We get a pulse, and then it waits, and we get a pulse, and then it waits, and we get a pulse when it waits. The current is there. It's just going the wrong direction. It'd be nice if we could use both halves of the AC waveform. And this is where our friend the bridge rectifier comes in. Remember, 4 diodes connected together in the circuit, which is known as a bridge rectifier. So let's connect the bridge rectifier to this thing. And there'll be a fuse here, F2 for sure. You would commonly call this the secondary fuse. F1, primary fuse, F2, secondary fuse. And let's connect it up to the bridge rectifier. So the bridge rectifier can be 4 individual diodes, or it can be a single one-piece bridge rectifier. They both work the same. So here's the positive output, where the 2 cathodes are tied together. That's the positive output of the bridge. So I'm going to connect that up to our motor. I'm going to connect the negative output to the other side of the motor. Watch carefully. These 2 wires are not touching. On a schematic diagram where you see 2 wires crossing each other like that, they are not connected. On a schematic diagram, if we want to show 2 wires that are connected, you will see a dot in the middle of it, which we refer to as a node. You'll see the node there. If the node is there, it means that those 2 wires are connected. If it's not there, it means that they're simply crossing over. Now, the way on older schematics, the way we used to draw this would be if we had a wire that was crossing another, we would draw this. Man, that's pretty obvious that that's meant to say, hey, those guys are not really touching each other. It's jumping over it. But when they went to like more modern kinds of drafting techniques, they opted for the node technique. So I'm going to trace the current flow in this thing. You absolutely do not need to know this. This is how it works because it's a class and I'm teaching you how it works. But you don't need to know how the current flows in order to be successful because you know how to test diodes. Remember that they test when they're good, open one way, junction drop the other, When a diode is bad, or almost any semiconductor is bad, really, they almost always short circuit. So when this side is positive and this side is negative, current flows this way through the fuse. I am now at the top node here. Will the current go through the diode on the left? No, it can't. There's only one way that it can go, and that's through this diode. Let's color it in red. This guy here. So it has to go this way. I'm now at this node right here. Can it go through the diode on the bottom? No way. It can only go this way down through the motor. So this is the source path. Gives the motor a little shove. Our load is the motor. Let's see what our return path is. So here's our return path. Returning. I'm returning. Uh-oh. So at this point, it appears that both diodes are facing the correct direction. But the current will only flow through one. Which do you think it'll flow through? The one on the top or the one on the bottom?
Bottom.
How many people think the top? How many people think the bottom? All right, so you're right, of course. Because current flows from positive to negative, not from positive to positive. Remember, voltage is pressure, right? So there's pressure pushing this way. How could this thing go against the pressure? It can't. It's not a salmon. It can't swim upstream. There's only one place it can go. And one place it wants to go is to negative. So it goes through this diode here and back to what is now the negative side. So notice we only use 2 of the 4 diodes now. But 100th of a second later, the polarity reverses. This side becomes positive. This side becomes negative. Let's trace the current flow. So now the current flows this direction. And we're here at this first node. It clearly cannot go back through the red diode, right? Not really red. It has to go this way through this one. Well, what I want you to see is this. Look what this diode is doing. Instead of just cutting off the current flow because it's going the wrong way, this diode is kind of acting like a detour. This diode is saying to the electric current, hey, buddy, come up here to here because I want you coming in the top of the motor. I don't want you going up the motor in this direction. That's the wrong way. I need you to go this way. So it kind of acts like a detour, brings the current up to the top here. We're now at this node. Clearly cannot go back through this, again, red diode. So it only has one way it can go, the same direction the first pulse went. So it goes through the motor, gives it another shove, and our return path is the same. Our return path is this way, up through here. And again, we're faced with a situation where both diodes seem correct, but it only goes through one. Naturally, it's the top one because we're heading to negative, like this. So that's negative. So that's the current flow. Whoa! But it doesn't make any difference if you understand that or not, because you're going to see 4 diodes connected together as a bridge rectifier, and it'll be maybe something like this. And when we get into other power supplies, we'll look at other ones. There are 4 diodes connected together, and that's a bridge rectifier. Or it's a single one-piece bridge rectifier. Do you have some chassis here? No? Can I see a chassis? This one has 4 individual diodes here. Never mind. Or it could be a single one-piece bridge rectifier. Bridge rectifier failure is not uncommon on older stuff. And it's pretty common on the older pinballs, that's for sure. But bridge rectifier failure is not uncommon. It happens sometimes. And again, you know how to test a diode. And a bridge rectifier is just made of 4 diodes. And naturally, they're rated the same way as diodes by voltage and current because they're made out of diodes. So if you needed a bridge of a higher voltage rating or higher current rating, you could certainly do that. So I forgot to mention to you that the previous power supply showed you that just used a single diode. My bad. I don't think I mentioned. It's called a half-wave power supply. The previous one I showed you with just one diode is referred to as a half-wave power supply. This one is referred to as a full-wave power supply because it uses both halves of the AC waveform. And what the bridge rectifier now has done is this. Here's the sine wave that we started with. What the bridge rectifier has done is taken the negative half cycles, redirected them, and flipped them up and made them positive. So instead of the sine wave looking like this, it's flipped up those negative half cycles, and this is what it now looks like. This is still shitty DC, isn't it? It's still pulsating DC. It still drops to 0 at every 0 crossing. It drops to 0 100 times a second. But we now have twice as many pulses in the same period of time. The motor would have twice the power that it should have, really, I suppose. And we're twice as efficient. Does that make sense? So this is called a full wave power supply. So far we've looked at two different ways to turn the AC into DC. A single diode is called a half wave power supply. A bridge rectifier makes it a full wave power supply, which is desirable, of course. There is another way that we can make a full wave power supply using just 2 diodes instead of 4. This is very, very common. And this is where our friend, the center tapped transformer, comes into play. If you remember, we just discussed this, that when they're winding the transformer, they'll stop exactly halfway through and pull out a loop of wire and then keep winding the coil like that. And remember, this is called a tap. It's called the center tap. So there is another way that you can make a power supply. It's a full wave power supply using just 2 diodes and the center tap transformer. In the center tap power supply, the center tap itself will be grounded like this. And we have 2 diodes. Like this, with their cathodes tied together. 2 diodes with their cathodes tied together. And let's hook up the motor. So there's the motor. Bottom side of the motor is hooked up to ground. Again, I'm going to trace the current flow right now. You absolutely don't need to know this because you know how to test diodes, but here's the current flow. I mean, here's how it works. When this side is positive, it's 4. When this side is positive and this side is negative, current flowing from positive to negative flows this way. So we know that it's definitely going to go through that diode. Can it go back to negative through this diode? No, it's reverse biased. So it only has one path, and that's this way through the motor to the motor. So again, that's our source path. The motor is the load, so it goes through the motor. Now check this out. Here's our return path. Our return path is back through ground and back up into the center tap. Notice we have only used 1/2 of the transformer here. The current leaves the top of the transformer, goes through the diode and the motor, comes back to the center tap. We only used half the transformer. 120th of a second later, polarity is going to reverse. This side's positive now, this side's negative. And the current's going to go this way through this diode right here. And again, notice what this diode is doing. This diode is a detour. This diode is saying to the current, hey buddy, come up here to the top. I want you going up to the top of the motor like this. Cannot go back through that diode. Would love to get there, but it can't. Right? So it's going to flow through the motor in this direction and give it another shove. And again, the return path is through ground and back up into the center tap. Notice in this case, we've only used 1/2 of the transformer again. So we've got like a pulse here and a pulse here. And if I were to look at the graph of the thing, it would look like this. We have a red pulse and a blue pulse. Obviously, they're not really colored. Red pulse, blue pulse. It's exactly the same full wave output as we saw with the bridge rectifier, but we're just using 2 diodes instead of 4. But we've had to make an enormous sacrifice here. What have we sacrificed, do you think, in this design?
Isolation.
What's that?
Isolation.
No, we haven't sacrificed isolation.
It's no longer floating.
No. I guess the clue is we only use half the transformer at a time. The current leaves them following the red path, it used the top half, following the blue path, it just used the bottom half. What have we lost here? What have we sacrificed? Not power, but you're close. What is it really?
That's amps.
No, it's the voltage, isn't it? Remember that it's the number of turns of wire that determine the output voltage, correct? If I'm only using half the number of turns at a time, I'm going to get half the voltage. Therefore, if I wanted to drive a 12-volt DC motor, the actual transformer would have to be a 24 volts center tap. That's what it's called, VCT. 24 volts center tap transformer. Because from the center tap to one side is 12 volts. Boom, a 12 volt pulse. From the center tap to the other side, a 12 volt pulse. It's going pulse, 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 like that. Make sense to everybody? So this is very common, very common. It's super common to use just two diodes in a full wave a full wave center tap power supply like this. It's super common. We're going to look at a bunch of examples of it as we go through the class. You'll see just a crap ton of examples. So those are the only ways that we make. Those are the only ways that we make DC. It's all done with diodes. We either use one diode as a half wave supply, two diodes as a full wave power supply, or four diodes as a full wave bridge rectifier power supply. Everybody with me so far? Okay, let's take 10. Let's take 10. Alexei, I'm answering your question. Where are you? I gotta wait for the guy that asked me. Alexei asked me a question during the break, and I want to explain it real fast. Where is he?
Yes, toilet.
Great.
Smoking.
No, we can't still do smoke.
This is why you don't smoke, right?
Now you see why smoking is bad.
Yeah, that's right. If for no other reason,
This is the real reason.
it makes people wait for you.
Wait, it doesn't mean
Yeah, look at me trying to redraw a better die.
That's the part, sir.
No, I just don't like it when I have to go to a train or something. There's somebody, without fail, that I have to smell their smoke. Like, just if you were in the path of any public transit, don't smoke. Because then I'm driving and I can't breathe. Can't breathe anymore.
Sorry. It's an interesting question, and I wish he was here to hear the answer. When he walks in, I think we should all give him a good round of applause. There he is! Yay! So during the break, I was asked a perfectly good question. Sometimes I teach this. Sometimes I don't spend the time teaching it. But it's a perfectly good question. And his question was really, how does a diode actually work and to let the current go through one way, but it won't let it go through the other? That's kind of the question, right? All right. So inside the diode, remember the diode is made of silicon. And pure silicon, like the chunk that I passed around, pure, and this is not as pure as the silicon would be in a diode, is an insulator. It's just a rock. It doesn't conduct electricity in either direction. Well, in a diode, we want to get it to conduct in one direction and not in the other. So when they're making that little chip that I showed you, they add what's called dopants to it. They're called dopants. They're small amounts of impurities, really, that they put inside this, if you remember, 99.9999% pure silicon. They add these dopants. So one of the dopants is phosphorus. Phosphorus has 5 electrons in its outer shell. If you remember from the homework, the different shells that are in an atom. Let me back up. Silicon has 4 electrons in the outer shell. And when silicon is refined into its pure form, it forms like a silicon crystal where they kind of share electrons. A full pure silicon crystal has 8 electrons in the outer shell. It's completely full. And that's what makes something an insulator. When the outer shell of an atom is completely full of electrons, it doesn't like to give electrons away, and it can't have any room for any new electrons, so it is an insulator, no electrons move. By adding a little bit of phosphorus has 5 electrons in the outer shell. There's an extra electron with no place to go. It doesn't have a home. And so those electrons fill the type N silicon. The type N silicon is full of these electrons, and the electrons are bouncing around. They're bouncing around looking for a home. They bounce around from atom to atom looking for a home, but there's no place at the end, and they keep moving around in what's known as Brownian motion. You don't have to know this. Just the heat of the room makes them just kind of bounce around. You can kind of think of it like a soup with a bunch of little meatballs floating around inside it. So that's the phosphorus. Boron, on the other hand, which comes actually from the desert near my house, from the Mojave Desert, boron only has 3 electrons in the outer shell. There's kind of a hole in the outer shell. It's missing an electron. And in fact, we call these holes, and they're positively charged. If I take a neutral atom, if you did your homework, you know about this. If an atom is electrically neutral, it has just as many protons as electrons, it's electrically neutral, and we take one of the electrons away, it leaves a hole in the electron shell and it makes the atom positively charged. Think about it. If I have a balanced atom and I flick away one of the negative components of it, what's left is positively charged. So on the other side, the type P silicon is positively charged. It has all of these, as we call them, holes. It has these holes, and the holes also move around. They jump around inside from atom to atom to atom. This hole moves from this atom to this atom and so on. So when you apply current in the right direction, when the diode is forward biased, if you remember that term, forward biased meaning it's on, current flows through the diode. It forces the holes and the electrons together and allows current to flow in ways that I'm not entirely sure of. Remember, I'm just a parts changer. I don't have a degree in physics or anything, but it recombines the atoms and allows the current to flow. If the electrons and the holes are pushed together at the PN junction, it kind of pushes aside the PN junction. Not ruins it, but when we put 0.6 of a volt on it, it's enough pressure to push through that very thin region. The PN junction is like a super thin region. I think they call it the intrinsic layer. I'm not quite sure. There's a super thin region that is the PN junction, remember, represented by the bar here. And it kind of, the pressure kind of pushes it aside and allows the current to conduct. So I'm not so sure about that explanation. I'm not sure I totally understand it. But what I do understand is this, and it's really obvious. When the polarity is reversed and the diode is reverse biased, meaning it's off and not conducting, it pulls the holes this way, away from the PN junction. And it pulls the electrons this way, away from the PN junction. Now we do not have the electrons and the holes kind of meeting each other at the middle. And what we're left with is this region right here, which is now made of electrically pure silicon, which is an insulator. We have electrically purified the silicon by reverse biasing it, and now we have a piece of glass right in the middle, and glass doesn't conduct electricity. So that's how the diode actually works. But, I mean, do you care? I mean, if you're interested in it, you do care. I think it's cool. But as for repair, do you need to know that? No, you just need to know how to test the diode and get a new one and stick it in there. So I hope that answered your question. I truly do. Because I can't spend any more time. So now we have three ways that we can turn the AC into DC using either 1, 2, or 4 diodes. So let me just redraw this. Here's the AC power, comes in the mains, the whatever it is. Here's F1, the fuse. Here's the primary winding of the transformer. Here's the secondary winding of the transformer. And let's just use a bridge rectifier. So let me draw a bridge rectifier back in. Oh, we should fuse it. And this time, I'm going to ground the negative output of the bridge rectifier, which is the way it really is. In the real world, when you look at a power supply, you open it up, the negative side of the bridge rectifier is grounded. And let's say, for instance, that we want to make, let me back up for just a second. Important thing about fuses, an important thing to understand about fuses, right? The fuse goes in between the source and the load. The fuse is in between the source and the load. The fuse is there to protect the source, not to protect the load. This is a really important concept. If I have some kind of a problem where I have, let's say, a couple of shorted diodes or something, it will blow the fuse. The fuse is there to protect the transformer from burning up, not to protect whatever the load is that's already shorted. The load fails first, drawing too much current across the fuse, blowing the fuse. It's a common misconception that the fuse is there to protect the circuitry. It's not. We have an expression in electronics that the source provides what the load demands. The source, whatever the source is, battery, power supply, whatever, transformer, whatever it is, the source provides whatever the load demands. What that means is that a source is kind of self-sacrificing. That is, if I have a shorted load, if I don't do something to protect the source will bust a gut trying to power the load. The source will sacrifice itself, it'll catch fire trying to power a shorted load. So the fuse is there between the source and the load, and the fuse is there to protect the source, not the load, which has already failed. That's the thing that blew the fuse to begin with. Is everybody with me on the concept? So if, for example, I had a problem where F2 was blown, could the transformer be the problem? No, it can't. The transformer must be good to be sending the juice through the fuse to blow it to begin with. If the fuse is blown, the transformer's not the problem. It's something over here, shorted diode or something else, a shorted motor on the load, or whatever the load happens to be, is drawing too much current, blowing the fuse. Does that make sense to everybody? That's really an important concept. All right. So remember that the output of the bridge rectifier is still pulsating DC. So while we could use this for lots of things, we could drive lights with it, motors and stuff like that, we really can't do anything really electronic with it, not really very much, because it still drops to 0 volts at every zero crossing. It drops to 0 volts every 100th of a second here in Europe and every 120th of a second in the United States of America. So we have to fix that, and this is where our friend, the aluminum electrolytic capacitor, comes into play. So the capacitor comes after the rectification scheme, whatever it is, whether it's 1 diode or 2 diodes or 4 diodes. The capacitor comes after that, like that. So this capacitor, this capacitor has a name, and it's referred to as the filter capacitor. This capacitor has a name. It's called the filter capacitor. Here in Europe, I have heard some people refer to it as the reservoir. The reservoir capacitor. That isn't how we refer to it in the United States of America. It's a reasonable term. I don't think it's the real term. I think it's called the filter capacitor, actually. So, since we can't use this for electronic stuff because it still drops to 0 so often, we add the capacitor. What the capacitor does is this. In fact, let me make this a little larger just so everybody can see it. This is, again, what comes out of the bridge rectifier. So when the voltage is at its peak, current is flowing out to the load. Remember, let's keep some perspective. It's a power supply, it's powering something. But at the same time, the current's going to flow into the capacitor, the filter capacitor, to charge it up. And you remember I made a big giant deal about how fast it should charge up and how fast it should discharge. That's the deal with capacitors. That's an indication of what its health is, how fast it will take the charge in and give it out. And remember, when its ESR increases, which we don't want, low is good, remember, it can't charge up quickly. You can see that because the current is only there at a peak for an instant in time. It has to charge up just like that. So when the voltage is at the peak, the capacitor is now fully charged. And you saw me charge it up real fast. Well, now the voltage starts to drop as it heads towards 0 down here. But we don't care now because the capacitor is fully charged. And the capacitor keeps the charge until the next pulse comes along and kind of tops it up. So when we add the filter capacitor, the effect is that it filters out the peaks and valleys, hence the name filter capacitor, and leaves us with the straight line that we've been looking for, which we now refer to as filtered DC. This is known now as filtered direct current because the capacitor, the filter capacitor, has filtered out the peaks and valleys, and we're left with the straight line that we've been looking for all along, which we now refer to as filtered DC. Hello, everybody with me so far? So we're making good progress. We started with AC, which we can't use at all, stuck one diode in there, made the motor kind of turn, stuck 4 diodes in there, turns great, but still drops to 0 volts. Now we add the filter capacitor, and we now have this beautiful filtered DC. It is not perfect, though. Because we have a load on this thing, because it is powering something, in between pulses, the voltage will drop as the capacitor discharges. I'm going to exaggerate the heck out of it here, but think about it. If I charge up the capacitor here, but now the voltage is dropping on its way to 0, and I'm sucking current out of the capacitor, the voltage drops a little bit. Then it gets topped back up and it drops a little bit. I'm very much exaggerating here. Tops it up, drops a little. So there is a little bit of changing voltage here that rides on top of the DC. And we have a name for this. This is an undesirable condition, and it is the way it works, but this is known as power supply ripple. This is called power supply ripple because if you look at it with an oscilloscope, it looks like this ripple line. It is a natural part of the way this works. Again, since we're discharging the capacitor in between pulses, the voltage is dropping a little bit, and then a hundredth of a second later, it jumps back up again, drops a little bit, and so on. So it is a slightly rippled line. This is sometimes also referred to as AC ripple, because it's kind of like a little bit of AC riding on top of the DC. So this is an undesirable condition. Remember, we're trying to simulate the output of a battery, which doesn't have ripple on it. You know, it's the purest form of DC you can get. So we're on our way, but we're not perfect. Well, here's an analogy for you if you don't fully understand this. When my wife and I go shopping, I really don't like to shop. I don't like grocery shopping. I don't like any kind of shopping, except for electronic parts. But, when it comes to grocery shopping, that kind of stuff, I really don't like to shop. So when we do our shopping errands at home, I drive the car, and then we park at a supermarket. And my wife comes in, buys whatever she wants, comes out, we load the car, go to the next stop, and so on. So when I'm driving along in the car, I can listen to the radio. Why? Well, because this is like a generator or an alternator in the car that's making the power, so I can listen to the radio. So right here where it's at the peak, that's like when the car is running and we're driving to the supermarket. When I stop the car, the generator goes off. There's nothing coming out of the generator. Can't I still listen to the radio? Of course I can, because the battery is charged and it keeps the voltage up there until it comes back in the car and we go to the next place. Does the battery discharge a little bit? Yeah, not much, of course. While I'm sitting there with the engine off? Of course it does. So when I'm sitting there, the battery's discharging a little, then we start the car back up. Woo! I'm charged. Stop the car, discharge, listening to the sport. Okay. Oh, start the car back up, and so on. So, so that's the way it works here. So it's not exactly perfect, but we're on our way. Is everybody with me on the concept here? So, as I've mentioned to you before, capacitor failure, as you probably know, is super common. Capacitor failure is just the number one problem in the world, electrolytic capacitor failure. And the way a capacitor fails, is not overnight. It fails a little bit at a time. As its ESR increases due to it drying out, it gets worse and worse and worse. And what happens is it allows more and more ripple into the power supply. As the capacitor's ESR increases, it can't get charged up fast enough. It can't discharge fast enough. And the ripple, and the bad capacitor, I should say, allows the voltage to drop further and further in between pulses. The point that I am making here, the important point, is that in a power supply, bad capacitors cause low voltage. Bad capacitors cause low voltage. That's the deal. When the filter capacitor fails, I kind of say when, not if, because they pretty much, they almost all fail eventually. When the capacitor fails, it allows the voltage to drop further and further and further in between pulses. So just keep this in mind, that when you have voltage issues where the voltage is too low, you got something going on, but the voltage is too low, you are almost always looking at bad capacitors under like almost all conditions. Because typically, like if you have a semiconductor failure in something, typically it doesn't work at all. It's possible, so, you know, something might work, but typically when a semiconductor fails, things just don't work at all. But as capacitors fail, things kind of get wonky. They kind of work, but either the voltage is low, or if it's a monitor, the picture starts to shrink. You get to a monitor, the picture's perfect. And then like 2 weeks later, you notice that the vertical size is shrunk. And then 2 weeks later, it shrunk even more and shrunk even more. And if you see this happen over a period of weeks and months and or years, it has to be a bad capacitor. That's just not the way semiconductors fail. Knowing how stuff fails really helps you get to the problem, really super fast. So,
and what's going on when it's go the other way around? So
if the voltage goes too high,
power supply goes up. Yeah, with the old Commodore 64s, with the original power supplies.
Oh, we're going to get to that because that's a switching power supply.
Yes.
And we're going to get into that, and I'll tell you exactly why. It is still caused by a bad capacitor, and you'll be amazed why it is. It's obvious how it's happening. It's part of the class. That's a great question. So anyway, so it's called the filter capacitor. And now we have a pretty good power supply. We have a pretty good power supply here. Again, let's say that we wanted to run a computer off it, which requires 5 volts. We can use a transformer to lower the voltage, bridge rectifier to change it into DC, slap a big filter capacitor on there. We're on our way, but we're still not there. We're still not there. There's a couple of reasons why not. One is, I guess the most important one is that the AC power here, the mains, is not particularly constant. It really depends on where in the world you live. In Brazil, it's really nuts. You know, I imagine in the Netherlands it's pretty fantastic. But it's not necessarily steady. But typically, by kind of definition, the AC power, the mains, can vary plus or minus 10%. I mean, we've all, I think, been in a room and had a compressor kick in and had the lights dim for a second and like that. Well, remember, the transformer is just giving us a ratio of input to output. If the input drops 10%, the output's going to drop 10%. So even if I make a transformer, let's say, and I've got like 5 volts, if the power, remember, can only vary plus or minus 0.25, a quarter of a volt. If this goes down 10%, 10% is half a volt, it's going to go down to 4.5 volts DC. That's below the minimum. The minimum is 4.75, right? If it went up 10%, it would go up to 5.5 volts. That's above the maximum. The maximum is 5.25, or 5.25. The lowest is 4.75. So sometimes things wouldn't work because the AC power would fluctuate. Well, that's silly. You can't have something plugged into the mains that sometimes doesn't work. I mean, that's nuts. And the other thing is that we have this problem with the ripple. We've got that little bit of ripple on the power supply. That's a problem. So we need to take it one step further. And so if you turn in your book to Understanding Linear Power Supply,
Part 2 is on 103.
95, maybe 95,
Yeah, 95.
maybe 95. And page 103 actually is the one you're right. Page 103 is what I really wanted you to see.
Could you correct it, just guessing here, could you correct the ripple with another capacitor?
No matter what if you had a giant capacitor bank, you could reduce it quite a bit. But since it's being discharged between pulses, it would have to be enormous and enormously expensive.
All right.
Yeah, that just wouldn't be practical. It just wouldn't be practical.
Maar dat doen ze dus op een andere manier.
You know, and really almost I guess probably everything that I'm covering here in the class is in the book. If you take the time to
voltage
look through it.
regulation.
Okay, so we have this problem with the voltage jumping up and down. So somehow what we have to do now is we have to regulate the power supply. We have to regulate the power supply, and what is meant by regulation in this case is voltage regulation. We have to regulate the output so that regardless of how the mains might fluctuate up and down, the output stays at exactly, let's say in this case, 5 volts. And the way we do that is with a simple device called a voltage regulator. One of the ways we can do it is with a simple device called a voltage regulator. So on the schematic diagram, it's typically drawn like this, just a kind of a box like this. And these regulators are known as 3-terminal regulators. They're called 3-terminal regulators. And they come in the same TO220 package that you see here as a transistor. It's the exact same package, but it's not a transistor, it's not a MOSFET, it is an integrated circuit. And what's inside is that. This is what's inside the voltage regulator. There's a ton of parts in there. There's some Zener diodes, as you can see. Remember, I mentioned to you the Zener diode is the thing that tells the voltage regulator, what voltage should I be? And this one has a couple of Zener diodes in it. It has a bunch of transistors. Like here's Q18, so it must have at least 18 transistors. We use the letter Q for transistors, by the way. We either use X in some cases, but really mostly they use Q for transistors. I know that seems stupid, but by the time they invented transistors, T already meant transformer. So a transformer, that's T1, let's say. They can't use T for transistors, so they use the letter Q, which seems really stupid until you know that one of the very first transistor packages was a round can like this, a round metal can. It has 3 legs coming out the bottom, emitter, base, and collector, and it has a little tiny razor sharp little piece of metal coming out to indicate that this is the emitter. When they designed this thing, they did something really stupid. They put the emitter, the base, and collector all 120 degrees apart. So it was 120 degrees apart. So it was impossible to tell which lead is which unless they marked it somehow. And they marked it with this thing that will slice your thumb right open if you're not careful. It's crazy. But from the bottom, it looked like the letter Q. So that's why transistors are Q. If you care, I don't know. You might think it's weird. Why is it Q? But that's why. Anyway, there's a bunch of transistors in here. There's a bunch of resistors. There are very few capacitors. You cannot put much capacitance on chip. It's just impossible. There's like a 20 picofarad capacitor. You used little picofarad sized capacitors in your kit, if you remember those little orange discs on the first kit, and same on the second kit, really. Picofarad is a millionth of a microfarad, meaning it's a millionth of a farad. They're itty bitty. kinds of things. So there are a couple of capacitors. Here's 4 picofarads, 22. But anyway, so all this stuff is inside that same TO220 package. The point that I'm making here is this. When you see some sort of a device, you cannot look at the device and say, oh, that's a transistor, unless you're familiar with the part number. You will see lots of devices, most of your work, you'll see lots of devices. You go, what is that? I don't know. It's in this package, but I don't know what this part does. The TO220 might contain a voltage regulator. It might even be a pair of diodes. Like on this power supply, which we'll talk about later on, this is a switch mode power supply. Right there, you see a couple of things in the TO220 package. Right here, those are those are devices in a TO220 package. But those are actually high-speed diodes. Those aren't transistors. They're not voltage regulators. Those are high-speed diodes. It's a dual diode assembly that we're going to talk about coming up. It's 2 diodes with their cathodes tied together, and 3 legs come out the bottom, and all of that is in that TO220 package, or those 2 things are in those TO220 packages. So it's kind of like when you go to Albert Heijn, you go to the supermarket, and there's all these different kinds of milk, which I was running around with the online translator going, oh, skim milk, okay, whole milk, Slachrum, yay. So whipped cream for those of you who don't speak Dutch. I love me some Slachrum. But anyway, so how can you tell the difference? You have to read the label. The packages are the same. So these TO220 packages, they're ubiquitous. They're all over the place. But what's in them might be a MOSFET, might be a bipolar junction transistor. In this case, it's an integrated circuit, and like that. So just kind of be really careful. Now, these are really cool devices. These voltage regulators belong to what's referred to as the 7800 series and the 7900 series voltage regulators. And we use these like crazy in games of the 80s, the early era of the golden age of video games. The 7800 series are for positive. They're for regulating positive power supplies. The 7900 series is for negative power supply. They're not interchangeable. But what's cool about this is the last 2 digits tell us what the output voltage is. So, for example, a 7805 is a plus 5 volt regulator. A 7812 is a plus 12 volt regulator. The same thing with the 7900 series. A 7905 would be a minus 5 volt regulator. A 7912 would be a minus 12 volt regulator. And in fact, you used one of these yesterday. One of the 5 thingies in the TO92 packages, the one on the edge, was a 78L05. It was a 78L, meaning low power, 05. It was a voltage regulator. What powered the kit yesterday? A 9-volt battery. What voltage does the IC need? It needs 5 volts to operate. So that little voltage regulator took the 9 volts and cut it down to 5 volts. And that's the way these things work. I'll say that this is a 7805. The way a voltage regulator works is really simple. Whatever you stick into it, it comes out as 5, in this case, 5 volts. Doesn't matter how the AC power varies up and down. No matter what it's doing, the output stays at exactly 5 volts. That's its job. It's a voltage regulator. That's what it does. And so the way it works is really simple. Now, I have to qualify that statement just a little bit. I cannot put 3 volts into a 5 volt regulator and get 5 volts out. There's always more voltage going into the regulator than comes out. And there's a minimum for that. The minimum is 2.5 volts. The input has to be at least 2.5 volts higher than the output for this thing to operate. In other words, for a 5-volt regulator, the input would have to be a minimum of 7.5. If it was a 12-volt regulator, it would have to be 14.5. But an engineer would never cut it that close. What if I put like that's a test point. What if I put 7.5 volts on the input, but the AC power dropped 10%? It would drop below the minimum and it would drop out of regulation. That is to say, if I put 6 volts into this 5-volt regulator, I might get 4 volts out, but it wouldn't be regulated. It wouldn't be. It would be wrong. So they always put plenty of extra voltage, like typically into a 5-volt regulator, typically they put in 12 volts or so, unregulated. Sometimes it's abbreviated UNR, unregulated. On the older Atari games, they referred to this as 10.3 volts DC, this unregulated input on the audio regulator board for the old Atari games. But when you measure it, it's like around 12 volts. But whatever it is, it's plenty high enough so that even if the AC power were to drop, we'd have at least 7.5 volts there, and it comes out as exactly 5 volts DC, and that's it. That's the power supply. That's an entire linear power supply. There are really only 4 sort of thingies in a power supply. Number 1, there is a transformer to change the voltage. Number 2, some sort of rectification scheme to change it from AC to DC using either 1 or 2 or 4 rectifiers. A filter capacitor, which is a very high failure. And some kind of a voltage regulator, which is not a very high failure at all. Not these 3-terminal regulators. We're going to get into other failures coming up here. But that's really all there is to it. Does that make sense to everybody? I mean, that's kind of how the whole thing works. Oh, it's noon. Okay. Well, let's take a break for noon for lunch. And how many of you really want to play down there for lunch? How many could just eat? Sorry, let me back up. How many of you can eat in half an hour? We'll pick up in half an hour. How many people really want to play? Nobody. All right. So let's take a half hour for lunch then, and I can use the time. My class, you know.
Yeah. All right, we're back.
So this next segment, I need you to put on your thinking caps. This next thing it's a really important concept to understand. It's simple to understand. It's not difficult to understand, but it's something that happens a lot. You need to kind of understand what's going on here. So, and this comes under the category of bad capacitors. Remember I said bad capacitors are a big giant problem. So I'm going to draw a couple of graphs on the board here. These are test points, like where you might just put your meter probe. I'm going to draw one graph that is the input side of the voltage regulator. Remember, inputs are on the left-hand side. I'm going to draw another graph that's the output of the voltage regulator. Remember, outputs are on the right. That's the way schematic works. Inputs are on the left, outputs are on the right. So I'm going to draw a couple of graphs here. So here's 0 volts, that's ground. 0 volts, that's ground. And when the regulator's working perfectly, and it's a 5-volt regulator, right, a 7805, we'll get 5 volts out. So let's say it's 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. So 1, 2, 3, 4, here's 5 volts. So when everything is perfect and the regulator's working perfectly, I should get 5 volts out. Does that make sense to everybody? It's a voltage regulator. That's what you're looking for. So let's look at the input now. 1, 2, 3, 4, 5. Yes, just 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. Let's call that 12 volts. And I'm going to draw another line here at 7.5 volts. Remember, that's the minimum, right? So 1, 2, 3, 4, 5, 6, 7. That's 7.5 or so here. So I'm going to draw a line at 7.5 volts. That's the minimum that we can put into this voltage regulator. So normally, when everything is working okay, remember the inputs are significantly higher than the output. So let's call it 12 volts. So we have 12. Oops, make that better. So we have 12 volts going into the voltage regulator. After we've rectified it and filtered it, it's 12 volts. Is everybody okay with this concept? Cool. All right. Now, remember, this line isn't really straight. It's really rippled. Because of that ripple, as I explained earlier, it's really a rippled line. It looks, if you were to look at it with an oscilloscope carefully, you would see, and I'm exaggerating here, it doesn't really look that much, but it's not exactly constant. However, remember that anything that's over 7.5 volts is going to come out as 5 volts, isn't it? So right away, the voltage regulator has eliminated the ripple. Everybody good with that on how that concept works? Anything above 7.5 comes out at 5. What happens to the extra voltage there? It gets turned into heat. Voltage regulators, they're called linear voltage regulators or 3-terminal regulators, change the extra current into heat. That's why you often see these things mounted on a heat sink, or you see a little heat sink mounted on top of the part, just screwed into the metal tab on the top of the device. So right away we've eliminated the ripple, but let's see what happens as the filter capacitor starts to age. And remember, capacitors don't fail overnight. It's not like yesterday they're perfect and today they're not working and their ESR is too high. It happens over a period of months and years. So let's say that the filter capacitor is its ESR is starting to increase, which we do not want. It's starting to fail. And instead of being 12 volts, it drops down to 1 volt to 11 volts, which is actually kind of a lot of ripple, really, 1 volt. But how does our output look? Is it still good? It's still good, isn't it? As long as we're above the 7.5, we're cool. So 6 months go by and the capacitor's getting worse. It goes from 12 down to 10, 12, 10, 2 volts of ripple. But how does the output look? It's still perfectly okay. So the capacitor can start to get pretty darn bad before you see any problem at all, because the voltage regulator cuts out this excess ripple that's coming in. So a year goes by and now it's 12, 8, 12-8, 12-8 like that. That capacitor is barely a capacitor at this point, but is it still working? Yes, we're above the minimum, so we still get 5 volts out. And that's how it's possible for you to sometimes look at power supplies and see that the capacitors are really domed, they're bulged, they're obviously horrible. That didn't happen yesterday. They've been bulged and domed for a year maybe, but you never saw the problem because the voltage regulator cuts it out. Is everybody with me so far? Let's see what happens though when we get disastrously bad. So the capacitor is a decade old or 20 years old or 40 years old in some cases in some of these things. And now the voltage is dropping from 12 down to 6, let's say. 12, 6, 12, 6, 12, 6, like 50% ripple. That is barely a capacitor at all. Well, now we will see a problem, but it won't be, it'll be very subtle. Here's the deal. Where it's above the minimum, we still get 5 volts out. Where it drops below the minimum, it drops out of regulation. But that's all that happens, just that. So it might drop down to 4 volts. Here it's 5 volts, 5 volts, 5 volts coming out. But here, boink, boink, it drops out to 4 volts. So this is all that happens. And it's real obvious when you look at it with an oscilloscope. And you just see these little dropouts. So it's going 5, 4, 5, 4. So now we have a real problem because, of course, the computer doesn't work. It needs 5 volts plus or minus a quarter of a volt to operate. And now it's dropping down to 4 volts. So you whip out your meter and you're going to measure the 5 volt power supply somewhere. You can measure it right across the power rails of the chip. As you probably know, on the printed circuit board, there are rails that carry the 5 volts in the ground to all the chips. Or you can just measure it at the power supply, whatever. You set your meter to read DC. The meter is not going to respond fast enough to show you 5 volts up here and 4 volts here. It's going 5, 4, 5, 4, 5, 4, but the meter is not going to respond fast enough to show you that. If it did, it would just be a blur. If the display was going 5, 4, 5, 4, 5, 4 every 100th of a second, you wouldn't read it, you'd just be a blur. Super important thing to know about the way a digital multimeter works. A meter will average the times that it's up high with the times that it's allowed to drop down because of the bad capacitor and show you some sort of an average reading between the two. In this case, it's going 5, 4, 5, 4, but it's not going to show you 4.5 volts. It's not going to average it that way. Since it's mostly at 5 volts and just drops down to 4 volts for a short period of time, it may show you something like 4.9 volts DC on your meter. But it isn't 4.9 volts exactly beautiful DC. It's really going 5, 4, 5, 4, 5, 4. You cannot tell the difference with a digital multimeter. This is what a lot of people use an oscilloscope for. Your little pen oscilloscope thing would work perfect for this. You'd see it dropping out. But the important thing to realize is that a meter is an averaging device. Anytime you're measuring a rapidly fluctuating signal, the meter is going to average the times that it's high and the times that it's low and show you something in between. Here's the pitfall that you need to not fall into. Remember that the integrated circuits that are in the game require plus 5 volts DC to operate, plus or minus a quarter of a volt, meaning, again, the highest it should be is 5.25 and the lowest it should be is 4.75. When you measure this with your meter, it's going 5, 4, 5, 4, the meter display is going to show you 4.9 volts. Doesn't that seem like enough voltage? It's more than 4.75. And you might think, oh, my power supply is perfectly good. I got 4.9, it's close enough. And if it's an adjustable supply with a potentiometer to adjust the output voltage, what do you think, Mr. or Ms. Technician, what do you think you're going to do when it's just a little bit low, 4.9? You're going to reach in there and you're just going to adjust it until it says 5 volts. And you'll be convinced that your 5 volt power supply is perfect. but it's really now going 6.4, 6.4, 6.4, 6.4, and it averages 5 volts, but it's not really 5 volts. Are you with me on the deal there? So it's very easy to make that mistake. Anytime you have a low voltage problem, if the thing was working perfectly yesterday and it's not working today, it's probably not an adjustment. You could try adjusting it up to 5 or 5.1, but it won't fix it in this case. It'll still be bad, and it may drive you nuts. And you may think that your problem is elsewhere. You may think, oh, I've measured the power supply. Oh, no, it's 4.9, or you've adjusted it, so it's 5. Oh, my problem's not the power supply. And now you're working on the board, or you're swapping boards, or you're doing something completely away from where the problem really is. So again, bad capacitors cause low voltage, number one. And number two, when you have a ripple issue like this, your meter's going to show you a lower voltage, but it isn't really constant. It's really going 5.4, 5.4, 5.4, and so on. Now, depending on the kind of digital multimeter you have, probably not the one I gave you in the class, in many cases on the linear power supply, if the voltage is low and you think you might have ripple in the power supply, you could switch your meter over to read AC volts. Remember I mentioned that the ripple is sometimes known as AC ripple because it's like a little bit of ripple of AC riding on top of the DC. What the meter will do is block the DC. When you put it on AC here, it puts a capacitor in series with your meter lead. And capacitors have an interesting property, I'll mention it again later on in the class, that they will block DC. Capacitors pass AC, but they block DC. So if you switch your meter to read AC and measure the power supply voltage, you should have 0. You should have 0 volts AC. But if you see a fraction of a volt of alternating current riding on top of the DC, you know you have a bad capacitor. That's the one and only thing that causes that, bad filter capacitor. So bad filter capacitor causes a problem with low voltage, Everybody cool on that? That's sort of a critical thing. It's really easy to be misled and say, oh, it's just low, I'm going to crank it up. Oh, no, I think it's perfect. But it's really not perfect. It just isn't.
But this was a scenario before this 7805, the regulator.
What about
it? This was a situation that you were...
if the capacitor goes bad, it allows the ripple in the supply. It's not the regulator that's bad, it's the capacitor that's bad.
No.
So bad caps cause low voltage, bad caps cause low voltage.
No.
Power supply ripple is also known as power supply hum. It's sometimes referred to as hum because if you're powering anything with a sound system in it and it has a bad filter capacitor, you'll have a noticeable, in your case, 100 hertz hum, something like that, coming from the speaker. If you ever hear that hum on anything that has audio, your home stereo or whatever, it's either humming because like the filter capacitor is bad, or it might be humming because it doesn't know the words of the song you're playing. Thank you. Tick your weight. That's my very best joke. All right. Anyway, so this is an entire power supply, and in this power supply, the things that fail are the transformer, which will not fail. It's extremely reliable. The bridge rectifier, which in some older stuff definitely does fail. In some older Atari games and Midway games, there's definitely bridge rectifier failures. This goes away in modern stuff. We're going to get to this later on today. In a modern power supply, the bridge rectifier is extremely unlikely to fail because modern power supplies have an interesting circuit, and I'll tell you about this later, called OCP, over current protection. These modern power supplies, if they are overloaded for some reason, a short circuit or whatever, they shut themselves off. Instead of burning up the bridge rectifier, which is what would have happened before, now they just shut themselves off. So modern gear, you don't see many bridge rectifier failures. Yeah,
so you've said modern several times. What exactly constitutes modern? Do you like the year?
So I guess what I refer to modern is probably turn of the century, year 2000, probably, and newer games, probably. Maybe even going back to 95. But before that, anything that has a linear power supply is a classic, not even 70s, but 80s, 90s, early 90s kind of machine. It's a good question. I'm not sure I even define that in my own mind. I think of it in terms of what the circuitry is. And we're not there yet in the class. All right. So anyway, bridge rectifiers are sometimes failure. The aluminum electrolytic capacitor is a very common failure. And the 7805, the voltage regulators, they are really well protected. And they have thermal protection. If they get too hot, they just shut themselves down. They certainly can fail. Let's see how you would tell if you had a bad regulator. So the voltage regulator itself, the 7805, one of the problems you'll have when you first start working on stuff is you'll probably know what you want to do. You just don't know where to do it. In other words, I want to measure the power supply voltage. Okay, you got 2 meter leads. Go. Where are you going to actually make the measurement? Well, in the 7805, the leads are arranged where the left-hand leg is the input, the middle leg is grounded, and the right-hand leg is the output. Input, ground, output. So if I want to measure the output voltage of it, all I have to do is touch my red meter lead to the output leg. The black meter lead is grounded to something that you find that is ground, like the negative side of the filter capacitor or the negative output of the power supply. It's pretty easy to find ground. The ground is kind of everywhere. Or even the metal chassis is ground. And I touch my meter lead to the right-hand leg, and let's just say for the sake of discussion here, right here on the output, it reads 3 volts, let's say. 3 volts. Instead of 5, it reads 3 volts. We have an expression in electronics, and the expression is garbage in, garbage out. Garbage in, garbage out. And what that means is that if you have a bad output from something, garbage out, maybe the input is bad. Certainly if the input's bad, you're going to have a bad output. So before you declare a part to be bad, it's supposed to be 5 volts coming out, it's 3 volts, I don't immediately say, oh, it's bad, it's supposed to be 5 volts, it's only 3 volts. Let's check the input. So you move over to the input, and what would I expect to come into a 7805? I'd expect something like 12 volts DC. Wouldn't you? I mean, I just finished discussing that. It has to be at least 7.5. It's going to be something significantly higher than that. So I expect 10, 11, 12 volts. So I move my meter lead now over to check the input. And this is a power on test, isn't it? So you have to be really careful. Honestly, you will not blow the voltage regulator even if you accidentally bridge a couple of legs together. It's protected. You wouldn't hurt. You would blow a fuse. If you grounded the input, if you grounded that input right there by slipping with your meter probe and shorting the input to ground, it very likely would blow up too. But it wouldn't damage the actual voltage regulator. So again, power on test, which I really don't like to do, but you have to do it. I mean, you have to troubleshoot the thing. So the left-hand leg should be 12 volts, and I measure the left-hand leg, and it's beautiful. It's 12 volts DC. What's my problem? Bad voltage regulator. It has a good input, it has a bad output, the voltage regulator is bad. And that's how you have to test it. There is no transistor test kind of thing like we've been doing with the meter for a voltage regulator. Your component tester won't test a voltage regulator. You have to, it only does what we call discrete components, individual components. So you have to test it with the power on, you have to test its functionality, you have to test it, you have to make it operate. So if the output's bad and the input's good, the voltage regulator is bad. Everybody with me so far? Pretty simple. Let's say you got to the output, measuring the output at that pin, at the output leg, and it's only 3 volts, but you move to the input, and on the input you only have, let's call it 6 volts DC or something like that. Well, remember, bad caps cause low voltage. Bad caps cause low voltage. The transformer really can't do that. A transformer can't just give you low voltage out. That just isn't the way they fail. It's a no-go. It's a go-no-go thing. A transformer is either working perfectly or it's on catching fire or putting nothing out at all, in my personal experience. So a transformer can cause the voltage to be low. Diodes, when they fail, short circuit. A diode never half-ass turns on. A diode will never be, oh, I have bad diode, so I'm only getting 6 volts instead of 12 volts. That's way not going to happen. When a diode fails, it's either working perfectly or it dead shorts. Or it's possible that it open circuits, but that's pretty rare. For a diode to open circuit, it has to kind of short circuit first and then burn itself open, which does happen sometimes. You see burn up diodes. It's not very common. No, the only thing that can cause the fact that this is too low has to be the filter capacitor. It has to be a bad capacitor. Does that make sense? That's the thing. That's how you diagnose that. If a diode were to fail, it would short circuit. And in a bridge rectifier, it's most common to have 2 short circuits. One of them short circuits first, and it actually takes out the other and blows the fuse. Again, as I mentioned earlier, the fuse goes in between the source and the load. If the fuse is blown, it is not the source that's bad. The transformer can't be bad if that fuse is blown. It has to be something on this side. Capacitors do not short circuit. Electrolytic capacitors do not short circuit. I've only seen one shorted electrolytic my whole life, and it was in a German telephone answering device in 1972. So I don't think you're going to see that. But and the voltage regulator likewise does not blow the fuse. There's just no way for it to blow the fuse. So most likely thing is that the bridge rectifier would have a couple of shorted diodes. Oh, I forgot one more scenario. Hang on a second. What if you were testing the output of the 7805 and it's 12 volts DC coming out? Woohoo! Well, that's way too high, obviously. If it has 12 volts DC coming out, it has to have 12 volts DC going in, doesn't it? You don't even have to measure it. That would have to be a shorted voltage regulator, which is really not common. I don't even think it's likely. I don't even think it's possible. I've never seen it. But theoretically, if the voltage regulator shorted input to output, that would put out way too much voltage. That can't be a capacitor problem, right? 12 volts we know is what's normal coming in. So all this stuff is good, right? If I measure 12 volts on the input of a regulator, all this stuff has to be good. It has to be the voltage regulator itself that's bad. And then finally, if you had a transformer failure, which you won't, but I want to cover it anyway, a transformer would either short circuit and blow the fuse or would open circuit. I have seen one open one. If I get to the output of the voltage regulator and it's 0 volts, it can't be a bad capacitor. Even if you pull the capacitor out of the circuit completely, we still have, remember, the pulsating DC. So it's not going to be 0 volts. So if it's 0 volts coming out, it really has to be 0 volts going in. But you would measure it. You say, oh, I've got 0 volts going in. I'm working my way back. Generally speaking, when you troubleshoot, you start at the output and you work your way back. In other words, why are you fixing the thing? Because the output's bad. Why? Let's keep going and let's keep going back. And when we get to good, what we expect, whatever's between good and bad, that's where your problem is. So if I measure 0 volts here, I've got 0 volts coming in. My next step would be, of course, to check the fuse. I guess I would do that first. To check a fuse, you should never, ever look at a fuse and call it good. You can look at a fuse and call it bad. You know, if you get a real blown fuse, you can see the inside of it's all black and like this, if it's blown to smithereens, as we say. Or if you can see that the actual fuse element inside is broken, okay, you can call it bad. Calling it bad is fine. Calling it good is a different story. Do not ever look at a fuse and go, that one's good, and put it back in. You have to use your meter to test it. You have to use your meter on the continuity beeper, the same beeper as the diode test, or the lowest ohm scale, the 200 ohm scale, and make sure it really is good. Because some of the what we call slow blow or time delay fuses have a center element in them that supports the fuse, and the fuse wire itself is curled around it, it's coiled around it like this. And when the fuse opens, when the fuse blows, it opens in open circuits. You may not even see where it's open. So are you with me on the concept there? It's really important that you never assume a fuse to be good. You could definitely assume it to be bad. Oh, it's bad. But don't ever call it good. So so I would check the fuses, and let's say the fuses are good. The next thing I would check, after checking 0 volts here and 0 volts here, I would want to check the output of the transformer. Would I have my meter set to read DC volts or AC volts at this point? AC, right? Transformer output strictly AC. So this is a common mistake that people make, where most of our measurements are DC. So I'm over here measuring DC, oh, DC. When I get to this point, I have to switch my meter to read AC because there ain't no DC in AC. If you accidentally had it set on DC and measured the output, your meter might show you 0 volts because there's no DC there, it's all AC, and you might mistakenly believe there's nothing coming out of the transformer when there really is. So I switched my meter to read AC volts, and I've got 0 volts AC. I put 1 meter lead here and 1 meter lead here. I am not using ground as a reference anymore. The transformer's not referenced to ground, is it? It's not hooked up to ground anywhere directly. So I don't have my black lead on ground and my red lead probing around. I am, with the power on, measuring somehow from here to here, which I could, if the fuse was good, I could really measure it at the bridge rectifier if I wanted to. And I find, 0 volts AC. There's nothing coming out of the transformer. Garbage in, garbage out. Garbage in, garbage out. So I have bad output from the transformer. What do you think my next step would be? Check the input of the transformer. And of course, that's the mains here, the 240 volts AC, or in my place, 120. And I measure right there across it, and it's beautiful. I have my 240 volts AC coming into the transformer, nothing coming out. The transformer would be bad. I've only seen one in my whole life, but that's how you test a transformer. You have an open circuit somewhere. You don't know where. It could be the secondary is open. It could be the primary is open. You could turn it off using a meter on ohms and ohm it out, but you can't get in there to fix it anyway, so why do you care which coil is actually bad? Well, I care because I'm a nerd, and I really want to know. Did the secondary open? Did the primary open? How is this possible? But we don't really care. We know the transformer. And the other thing would be if fuse 1 is blown. If fuse 1 was blown, but fuse 2 is still okay, the next thing I would probably do is remove F2, just pop it out. If I remove F2, just for troubleshooting purposes, I have completely eliminated everything else in the circuit, have I not? None of that stuff is hooked up now. So just by pulling that out, I'm sure that my problem's not going to be there. And then if I replace F1 and it blows again, the only thing hooked up to it is the transformer. It would have to be a short circuit in the transformer somewhere. Make sense to everybody? So there really are only 4 parts to this, really, and the transformer won't fail, and the capacitor probably will. The diodes might. The voltage regulator, not really very likely. So that's all there is to a linear power supply. We do the same thing in monitors. In some of the monitors, the voltage regulator it's not exactly a 3-terminal regulator. It's got some other leads coming out the bottom, but it's the same kind of a thing. For example, we have these regulators, part number STR130 or STR123. They're used to make the higher voltage power supply required by a monitor. In a monitor, remember we are really talking about monitors now. In a monitor, the main power supply is referred to as the B+ power supply. it's called the B plus, and if I say, when we're working on monitors, if I say, well, what's your B plus? That's the main power supply in a monitor. The term is actually a throwback. Remember I mentioned the old radio days where radios were vacuum tubes and they had batteries, and they had 3 batteries. They had an A battery that operated the little filament or the heater inside the tube. They had a B battery that was the main, what's called the plate supply, the main high voltage power supply. And they had a C battery that was what's called a bias supply. It's anyway, when they finally made the battery eliminator, the power, what we call now a power supply, they still kept the term B, like the B battery, meaning that this is the main power supply. So the main power supply is called the B plus power supply. So in a monitor, this is very common where the input here is maybe plus 160 volts DC or something, and what comes out is plus 130 volts DC. It's the same kind of integrated circuit regulator, and troubleshooting is exactly the same. It works exactly the same way. Before they developed this kind of regulator, though, they had to do it with transistors. So I am now going to be getting into a more complex, we're really starting on complex stuff now. So I hope you're kind of awake here for this. The 3-terminal regulator is a great thing. It really is. But it's kind of limited. It's limited, number 1, to voltage, and number 2, by the amount of current it can handle. Like the little TO220 package, 7805, can only handle an amp of current, and the highest voltage is 12 volts. And monitors require much higher voltage and more current. So there's another way that we make that we regulate power supplies. Let me just draw half the bridge rectifier. I'm just save some room. So there's the bridge rectifier. There's the filter capacitor. The filter capacitor is easy to identify. It's always the largest, the physically largest capacitor is the filter capacitor. So instead of using an integrated circuit voltage regulator, we can use, and we do use transistors. Before they invented the voltage regulator integrated circuit, they were making regulated power supplies out of just individual discrete components. And so instead of using a voltage regulator, IC, we can use a transistor as a voltage regulator. And typically it's an NPN transistor, and it's a circuit like this, where the unregulated voltage comes in. Let's call it, let's say it's a low voltage power supply. Let's say it's 12 volts DC unregulated, meaning, the transformer's over here and the AC power can jump up and down and stuff like that. And then this is the output that goes to the load, whatever we need to drive with this power supply. How can we use a transistor as a voltage regulator? Well, remember I mentioned to you that a transistor can be all the way off, or it can be all the way on, or it can be anything in between the two, from all the way off to all the way on. So let's think about this for a second. If this unregulated voltage is 12 volts, let's think about it for a second. Remember, this is the collector, this is the emitter, and when it's off, there's no connection between collector and emitter, and when it's on, the collector and emitter, when it's fully on, they're connected together. If the transistor was completely off, what would my output voltage be here on the emitter? If the transistor is completely turned off? It'd be not nothing, but 0, right? 0 volts. Why? Because it's off. It's an open circuit there. There's no current going out, and it would be 0 volts. So if the transistor's all the way off at 0 volts, what would the output voltage be if the transistor was totally on, if it was saturated, meaning it was totally on and the collector was connected right to the emitter? It would be 12 volts, wouldn't it, right? If the transistor is fully on, the collector is connected to the emitter, and we get 12 volts out. But let's say we want 5 volts. We want exactly 5 volts DC out to power all the stuff in the game, all the IC chips, computer chips in the game. all we have to do is put approximately 5.6 or 5.7 volts on the base of the transistor. If I put let's use 0.6 because that's, the book probably says 0.7, but let's use 0.6. If I put 5.6 volts on the base of this transistor, the output has to stay at exactly 5 volts. When I said to you that it takes like 0.6 volts to turn on a transistor, I didn't give you the whole story. The transistor really compares its base voltage to the emitter. In order to get the transistor to turn on, the base has to be 0.6 of a volt higher than the emitter. It really compares itself to the emitter. In other words, I can put some voltage on the base, and the base goes, okay, you put 0.6 on me, let me check with Mr. Emitter. Oh, emitter is 0, okay, I'll turn on. So it's really comparing itself to the emitter. It's the difference in voltage between the base and the emitter. So that has to be 0.6 of a volt to turn it on. Let's imagine for a second that this voltage was less. Let's say it was 0.55. I'm explaining this backwards. Let's just say for the sake of discussion, so if I put 5.6 volts on the base, the emitter has to stay at exactly 5 volts. Let's say that I put less voltage on the base. If I put less voltage on the base, the output's going to drop. If I put more voltage on the base, the output's going to increase. It always has to be exactly like 0.6 or 0.7 different between the base and the emitter. So all I have to do to get 5 volts out of this thing is to somehow peg the base voltage at exactly 5.6 volts. If I can get 5.6 volts on the base, the output has to stay at exactly 5 volts. So one way that we could do this is with a Zener diode. Remember, the purpose of a Zener diode is to keep the voltage exactly constant. So if I hung a Zener diode on here and made this voltage exactly 5.6 volts, I get exactly 5 volts out. Now I do have to somehow feed some voltage into there. So we take a little bit of this voltage, run it through a resistor of some value, we don't care, and connect it to the base. The Zener diode keeps that voltage at exactly 5.6 volts. If I have 5.6 volts on the base, the emitter has to stay at exactly 5 volts. If, let's say, the voltage were to drop for some reason, I put less than 5.6 on it. If the base voltage drops, the difference between the emitter and the base is more, and that turns the transistor on more and boosts the voltage back up to what it should be. If for some reason this voltage is higher, now we have less voltage on the base compared to the emitter, and the voltage has to drop back down again. So no matter what, the transistor is going to keep that 5.6 volt difference on it. We're going to get exactly 5 volts out. So this is the way the very first XY monitors were built. The very first vector monitors that were in like asteroids, they built the power supply like this. They made a plus and minus, I think it was a 40 volt power supply. This is very wasteful and very simple design. And in this circuit, that Zener diode was always drawing a lot of current, and this Zener diode would fail all the time. It's just not a very good system. Now, somehow we can take the load off of this thing. We can make a better system for doing this. And again, the idea here is that we need to keep the base at exactly whatever voltage we want. In other words, like in a monitor, if this was, if we want 120 volts DC out, what voltage would I put on the base? 120.7 or 0.6 or whatever it is. The base always has to be 0.6 of a volt higher than what you want to go out. So this kind of a power supply which is what you see here. This is a Hanter-X monitor. This kind of a power supply has a name. This kind of a power supply is known as a series pass regulator. This kind of regulator, I should say, is known as a series pass regulator. And it's how we did things for a long damn time, decades and decades and decades. Series pass. It's called series pass because this transistor is now in series with the load. Remember, for the 20th time now, in a series circuit, current flows through one thing to get to the next thing, right? And it passes all the current through it. So this transistor is known as the series pass regulator transistor. So let's look at this exact thing in a Hanter-X monitor. This is in your book, in your big green book, if you care to follow. You don't have to, on page 25. In fact, let me even make it a little bigger, I think. Yeah, here we go. So let's see what we see here. Here's where the AC power comes in. In this case, they measured it at 128 volts, which is really bizarre. When they put voltage readings on a schematic, sometimes they just pull a sample unit off the line and measure the voltages and write them down. If their line voltage happened to be 128 volts at the time, that's what they wrote down. That isn't very standard. But there's the AC power coming in, and it goes to the bridge rectifier. It's drawn differently than I've drawn it, and it does have some little capacitors across it, but for noise abatement. We'll talk about that in just a little bit. But here are the 4 diodes. In a bridge rectifier, there are 2 diodes with their anodes tied together, and there are 2 diodes with their, 2 diodes with their cathodes tied together. That's the positive output. And 2 diodes with their anodes tied together. That's the negative output of the bridge. Well, this is just another way to draw a bridge rectifier. Anytime you see 4 diodes in connected together, it's a bridge. But, what are we looking at? Here are the 2 diodes where the positive leads come together, D21 and D22. Here are the 2 leads where the anodes are tied together. That's the negative output. And you can see that's the ground symbol, the euro ground symbol. And the AC power goes into where there's one of each, where there's an anode and a cathode tied together. That's where the AC power comes in. So it's pretty easy to recognize how the thing is hooked up. So there's our bridge rectifier, and it's you have that chassis? Is that an MTC 900 or? Yeah, it's an MTC 900. Huh? Oh, this is here. So that's these guys right here. There are the power fuses right here. And there are the 4 diodes that make up the bridge rectifier. In this case, it's 4 individual diodes. Nothing mysterious about it. Right? There's the filter capacitor. Remember that the main filter capacitor is always the biggest capacitor in the whole thing, and there it is. Right? So on the schematic, AC power comes in, goes to the bridge rectifier. It does go through a low ohm resistor first before it hits the filter capacitor. Okay, wake up, wake up, wake up. In my experience as a technician, anytime I see a low ohm high watt resistor, in this case it's it says 2R2, that means it's 2.2 ohms. I forgot to mention this to you when we were talking about resistors. Sorry, let me back up for just 1 second. If I had a resistor that was 1.2 kilo ohms, remember that might be 1K2. Remember and the kit you built yesterday had a 3.3, I think, 3K3. If this resistor happened to be, let's say, 2.1 megohms, that would be 2M1. But if it's just straight resistance, just straight ohms, let's say it's in this case, 2.2 ohm resistor, it's 2.2 ohms. It's shown as 2R2, meaning R meaning just straight resistance, no, not kilo ohms or not megohms. Everybody okay on that? So anytime, so the AC power is rectified here. It does go through this low ohm, high wattage, 17 watts. So it's a ceramic wire wound resistor. I guess I'll find it in just a second. Before it hits the main filter capacitor. Let's see if I can quickly. Is that you? I think it is you. I think it's this big ass one right here, isn't it? Right? This giant ceramic resistor. And then it goes to the filter capacitor. Well, anytime I see that, it raises a red flag for me. And very often I'll throw a meter on it just for shits and grins, as we say. Just because it's there and I know it's a common failure. Let me reiterate this. Anytime I see a low ohm resistor, 1.2 ohms, 2.2 ohms, 2.7 ohms, something like that, in series with some kind of power, I'm always going to suspect that might be bad. And when they fail, they open circuit. Remember, when resistors fail, they open circuit. So if anything short circuits over here, there's a possibility it will open that resistor. What happens to you in the real world is you find whatever shorted over here, horizontal output transistor will get there, or some other flyback transformer, something bad has happened to the monitor there, and you fix that, and you go, oh boy, I fixed it, let's fire that sucker up. And you plug it in, and it's dead as a doornail. It doesn't do a darn thing. And then you have to troubleshoot the power supply. You find out, oh, I don't have my 130 volts. And you find out that resistor is open. So if I see the resistor or something like that, I often just throw a meter on it just because I know that it's a common failure. In this case, there is a reason for this resistor here. This is very common to see, a low ohm resistor in series with the power that is going to the capacitor. There is a thingy that destroys electronic components when you first plug something in. And it's a phenomenon known as inrush current. It's called inrush current. If you're old enough to remember incandescent light bulbs before LEDs, you probably know that the most common time to have a light bulb fail is when you first turn it on. When you first turn it on, it just goes pop, and you go, what the hell, was working yesterday, now it's blown up. The problem is inrush current. When you first turn something on, a lot of current rushes in to get the thing up and running. In the case of the light bulb, the tungsten element itself has a lower resistance when it's cold than when it's hot. So lower resistance means more current, and it blows it up. But in this case, it is to protect the filter capacitor. In this case, the resistor is here, like there. It's to protect the filter capacitor. I shouldn't say that. Sorry, I misspoke. It's not to protect the filter capacitor. It's to limit the inrush current going into the capacitor so you don't blow the diodes. These might be 2 amp diodes, but when the capacitor is fully discharged and you first plug it in, a whole bunch of current rushes in to charge up the capacitor. Momentarily, the inrush current might be 10 amps, and it'll blow the diodes on the bridge rectifier. So to prevent that from happening, just by design, the Italian people that make Hantrek said, hey, we're just going to put a resistor in series with that sucker and limit the inrush current to the capacitor. But it turns out to be not an uncommon failure, that the inrush current limiter fails. I am going to show you a whole bunch of this tomorrow when we start looking at monitor schematics, and you will see that in a monitor, there's a whole bunch of power supplies that are protected by these like 1.2 ohm, like 2 watt resistors that fail a lot. They fail a lot. And we're going to talk about those tomorrow when we get to the monitor. Again, they're to kind of, they were supposed to be protection devices to limit inrush current, but in fact, they themselves are the things that fail sometimes, usually because something else is there, right? So anyway, so getting back to this, right? So the AC power comes in, we turn it into DC, we filter it with a filter capacitor. Now we have this unregulated voltage right here. And this voltage will be pretty high. Even though we put in 128 volts according to this, that voltage coming in there is going to be about 170 volts or so. This is something that's very important to know. Wake up, wake up, wake up. Anytime I turn AC into DC, the DC that comes out seems to be higher than the AC I put in. It isn't really, but what is meant by that is this. If I put in 120 volts AC, rectify it, filter it, this voltage right here will be approximately 165 to 170 or so volts DC. What? Yes. I put in 120 volts AC, I rectify it and filter it, and all of a sudden it's magically higher than what I put in. It is not. You need to wake up and listen to this explanation. It's really important. Measuring DC is easy. You know, whenever you measure it, it's always the same. Whenever it is, it's always the same. DC is easy to measure. But AC looks like this. This is the answer to your question. AC looks like this. How the hell are you going to measure something if it's always changing voltage? Sometimes it's 0 volts. Sometimes it's at some kind of a peak voltage. The rest of the time it's less than the peak voltage. How the hell are you going to measure something like that? Well, it turns out that there are several ways that you can measure alternating current. One is to measure from this peak to this peak. That's a measurement we refer to as peak to peak. It's called the peak to peak measurement, or PP. Sometimes it's listed on the schematic. Peak to peak, right? But peak to peak measurements are generally reserved for what we call non-repetitive waveforms. Stand by. A sine wave is a repetitive waveform. It repeats, does it? It's the same. Every time the thing in the turbine spins around once, it gives you the sine wave. So it repeats the same thing over and over again. It's a repetitive waveform. And the negative peak is just exactly the same as the positive peak. It's always the same. Generally speaking, not always, but generally speaking, we reserve peak-to-peak measurements for things like audio. If I were to graph audio, if I were to take a microphone and hook it up to an oscilloscope, it might look something like this. Here's where it's loud, here's where it's soft. Here's where it's loud, here's where it's soft. Well, as an audio guy, if I'm in the audio business, which was one of the things I used to do, I need to know the peak. I need to know the maximum that's coming in so I don't have a problem with my mixer board or my amplifiers or whatever. If it comes in too hot and heavy, it can clip the sound and make it sound all distorted and crappy like that. So I really need to know the whole measurement from peak to peak. I need to know what I'm looking at. But in a sine wave is repetitive. So I really only need to measure one peak, from 0 volts to one peak, and that's the peak measurement that you were asking about. How do we measure it? We don't measure it from peak to peak. When we're talking about AC power, the 240 volt mains is this. The height of this thing, remember the higher it is, the higher the voltage, has a name. It happens to be called the amplitude. A-M-P-L-I-T-U-D-E. The amplitude is the height of the waveform. It's the voltage, really. But we gotta fancy it up, so we call it the amplitude. Well, what's the amplitude of your input? You know, it sounds fancy, right? So if we just measure the amplitude, the voltage, between 0 volts and one peak, we know the voltage because the negative peak is exactly the same. So that is simply referred to as the peak measurement. It's called the peak voltage measurement. And when we talk about AC power, the mains, that's what we're talking about. We're talking about the peak measurement. How high a voltage is it? Like that. Well, when we rectify this, remember what the bridge rectifier does? It did that, right? And then we filter it with a filter capacitor. The filter capacitor keeps the voltage at the peak. Well, when we're measuring AC, remember that's a rapidly fluctuating signal. And I sort of jumped up and down just recently and said, hey, the meter's an averaging device. If you check a rapidly fluctuating signal with a meter, it's going to average the high times and the low times and show you something in between. And that's how we measure AC. When you put your meter on AC and jam these meter leads into the holes, what you're reading is an average reading. 232 volts. But that's an average of the times that it's up high at the peak with the times that it's lower. It's the average reading. And it's a special kind of an average. It's a special kind of a mathematical average that we use in electronics, and it happens to be known as the RMS average. It's called the RMS average. It happens to stand for, you absolutely don't need to know this, root mean square. It happens to stand for root mean square. And it's some kind of a mathematical thing that eludes me, where you take the square root of the peak voltage, you add your mother's age, and divide by 6 if it's Tuesday. I don't really know what it really is. But it turns out that the RMS average for a sine wave, the RMS average for a sine wave is 0.707 times whatever the peak voltage is. So when I measure this thing, and my meter now says it's 230 volts, that's an average measurement. It really peaks at the inverse of that. It really peaks at, in this case, 232 times 1.414 volts, which is the inverse of the RMS, and it shows you the peak voltage. So when we rectify this, turning it into pulsating DC and filter it, the filter capacitor keeps the voltage at the peak, which of course is higher than the average reading that you have here. So that voltage didn't come from nowhere. It didn't really magically turn a lower voltage into a higher voltage. That voltage was always there to begin with. You just never saw it because the meter is averaging them out. But once we rectify it and filter it, that voltage is 160 or 170. So that's a completely normal thing. That's completely normal. There's nothing that could fail to cause the voltage to go too high, only too low. Capacitor failure, right? So my point is, don't be surprised at all if we check the voltage across the filter cap, the main filter cap, and it's like 160 volts. And you also have to be a little bit cautious about this. Depending on what kind of monitor it is, some failures when you unplug the monitor can leave that main filter capacitor fully charged at 160 or 170 volts, or here 320 volts, depending on what kind of monitor it is. And it will shock the hell out of you. If you touch it, it just shocks the living daylights out of you. It just shocks you like crazy. So you have to be careful about that. But so getting back to this here, and comparing it to the hand direct power supply, AC power comes in, goes to the bridge rectifier, goes through that low ohm, high wattage resistor. There's the filter capacitor. If we follow this line, this is now, we'll have 165, 170 volts on it. Here's the series pass regulator transistor right here, transistor number 20, TR20 in this case. It goes into the capacitor, goes into the transistor collector, comes out the emitter, and it comes out at 130 volts. So our voltage regulator is that actual transistor itself. That's the main voltage regulator, which is this guy right here on the side, this transistor right here. So the AC power comes in, goes to the bridge rectifier, filtered by the filter capacitor, and regulated by this. It's not an integrated circuit. It's a regular transistor, regular old transistor. So something has to tell that transistor what voltage to make. Something has to tell that transistor what voltage to make, and that's what the base is for. The base voltage determines the output voltage. So if we want 130 volts out, all we have to do is stick the base at 130.6 or 0.7, and the output will stay at exactly 130 volts. And that's the purpose of the rest of the circuitry that you see here. These two transistors together form a circuit, a very common circuit that we use a lot in the amusement games and the old pinballs and in all of the old monitors. A combination of two transistors with their collectors tied together, and the emitter of one transistor goes to the base of a second transistor. You know, again, I promised you we're going to get more complex as we go through the class. So here's the deal. There is another transistor here connected like this. This circuit, which consists of one transistor essentially driving the other, has a name. It's called a Darlington circuit. D-A-R-L-I-N-G-T-O-N. It's called a Darlington. The Darlington may be two individual transistors, or it may be a single one-piece transistor. There's a common transistor we use in pinballs. It's a TIP122, and it's an actual Darlington transistor. Inside the transistor, inside the package, there are actually two transistors. The emitter of one goes to the base of the second one. The two collectors are tied together, and all of this is in one transistor package. It's two transistors in one. The advantage of a Darlington transistor is high gain. The Darlington, by the way, was invented by a guy using vacuum tubes, a guy named Darlington, obviously, to do the same thing. I'm sure he's dead now. So the advantage of it is high gain. Do you remember we talked about gain, the beta of the transistor? And in fact, the device that you made measures the beta, doesn't it? Did you notice that when you put in your bipolar junction transistor, it said B equals 87 or whatever it is. That's the gain of the transistor. Well, in a transistor, the more current that flows through a transistor, the more current it takes on the base. By adding the second transistor in a Darlington circuit, we way reduce the amount of current that we need to drive the thing. In a Darlington transistor, the gain of the first transistor is multiplied by the gain of the second transistor. So, like, if this big transistor, let's say, had only a gain of 100, which it might, it's a high power kind of a low gain transistor, but this transistor has a gain of 100. Together, the thing has a gain of 10,000, doesn't it? Like 100 times 100, right? 10000, yeah, 10,000. So the beta would equal 10,000. What that allows us to do is use a very tiny but accurate other circuit to drive it and to get our plus 130 volts out. So this is the Darlington part of it. Transistor number 20 is the actual series pass regulator transistor. There's another transistor that drives it. I won't bother showing it to you. Okay. So all we have to do is this. If I want 130 volts DC out there, what voltage will be on the base to get 130 volts DC out? 130.7, right? The base has to be 0.7 higher than the emitter. So we have 130.7 there. To get 130.7 out of there, what do I have to put on the base here? 0.7 higher than that, or 0.6 or whatever. So I'd have to put 131.4 volts, I guess, or so, on the base of this one, and that would give us 130.7 coming out of this one to the base, which would give us 130 volts out. So this is an absolutely standard voltage regulator configuration that I could open up a dozen old power supply schematics for older monitors, and you would see this exact same circuit. So now something has to tell the base of that transistor right there. That has to have the 131.4 volts on it. Something has to tell it that, and that's the job of the rest of it. See the Zener diode down here? This transistor and the Zener diode combination form a circuit known as the error amplifier. Remember, the purpose of the Zener is to keep the voltage constant as a voltage reference. So this thing happens to be, you don't really have to know that it's called the error amplifier. But this is the circuit that's going to tell the base what voltage to put on there. Depending on how much this transistor turns on, the more it turns on, the lower the voltage will be on the base. The less it turns on, the base voltage will allow to rise, since it's got a network of resistors here, or I guess it's this one, that pull the voltage up. So what this is doing is sniffing the output. Think about it for just a second. Somehow a voltage regulator circuit has to kind of sniff the output so it knows what its voltage is. If the voltage goes too high, it's got to come down. If it goes too low, it's got to come back up again. So that's what this is doing. Look, it's connected to the output. This is the output of the voltage regulator circuit. It's clearly labeled plus 130 volts DC. So it takes some of that output, runs it through a resistor here, another resistor here. I don't know why they use two 16K resistors in series. I guess they needed 32K, and they don't make a 32K resistor. So I guess that's what they needed for whatever reason. And that feeds the base. So that is how this thing is sniffing the output. Remember, the base of a transistor is the input, isn't it? So if I just kind of sniff the output here by running it into the base of this transistor is comparing that voltage it receives on the base with the voltage it knows is on the emitter, because it's a Zener diode, and that's going to stay exactly constant all the time. And it turns on just enough to make that voltage 131.4, which makes that voltage 130.7, which makes that voltage come out at exactly 130. I'm not sure what this other transistor is doing. I think this transistor is a part of an overcurrent protection thing. I'm pretty sure now that I look at it, that if you have some kind of a short circuit on this line, it drags that emitter low, turns the transistor on, and reduces that base voltage. It kills the power supply. Yeah, now that I look at it. But even if you don't know how any of this works, let's say none of what I just said made any sense. Oh my God, what? I don't even know what it is. Think about it logically for just a second. If I check the output voltage, and it's supposed to be 130 volts, but I only have 70 volts DC, pretty low voltage. It could be a bad capacitor, and change or look at the capacitors. They're all good. Real troubleshooting with the power on, if I measured the input voltage right here, and I found it to be a plus 165 or so, remember that's what I expect, but the output voltage of the regulator is only 70. Doesn't it make sense that my problem is in that circuit somewhere? Just think about it logically for a second. If you treat this as a black box, doesn't it make sense if I have a shitty output, but the input's good, garbage in, garbage out, my problem is in here somewhere? Everybody with me on the deal? Well, now I especially really don't want to be poking around there with the power turned on. Yes, I could. With the power turned on, I can ground my black meter lead and measure the voltage here and here and here and measure the voltage across the Zener, or I could turn it off and check all the parts and like that. That's what I'm going to do. I could do it. I know how to do it. I can just easily check all the voltages and come up with the exact problem. Or I could safely, easily, with the power turned off, since I know the problem is either this transistor, this transistor, this transistor, or the Zener, or this transistor, or the Zener, which tests like a regular diode, why wouldn't I do that? I can do it safely with the power off. If I check a transistor in circuit, it doesn't check right, I can unsolder it and take it out. Safe. Oh shit, it's good. Put it back in, move to the next transistor. Are you guys all with me? That's all you have to do. That's all you have to do. You don't want to do a lot of power on testing, I don't think, but this is well within your abilities to do this kind of thing. Does this make sense? Now we can look at this exact same circuit in a bunch of monitors. I'm really not going to do it. I mean, we can tomorrow when we see it. I'll go, hey, look, there's another circuit like that. But this series pass regulator is extremely common, and that's how it works. In the more modern power supplies that use an integrated circuit, remember I said that there was that STR-130 integrated circuit. All of this is replaced by that integrated circuit. I showed you the schematic of the 3-terminal regulator, how all the stuff that's inside it, more modern than this, monitors use that integrated circuit, which is a high failure item. We'll talk about this more tomorrow. The voltage regulator integrated circuit in lots of monitors fails a lot, and we'll talk about that later. So let's take another break. I got 1:45 here. Let's take a break for 10 minutes and come on back and we'll continue. be the schematic diagram of the exact same circuit in an electro monitor. I just want to show you the similarities. It's pretty obvious. You put 120 volts AC in. There's the bridge rectifier. There's the filter capacitor. The unregulated voltage comes up here through another fuse to and a low ohm resistor to the collector of one of the two Darlington transistors. It also goes to the collector of the main series pass transistor, the big one on the side. And coming out of the thing is 120 volts, and this is the rest of it. There's the Zener diode in the exact same spot. There's the error amplifier, same as we saw before. It's just the same circuit. It just doesn't have the overcurrent protection, but it's really the same circuit. Now, before we move on to switch mode power supplies, I want to go back and explain something a little more about the isolation transformer. It's a weird thing for a lot of people where they just don't understand why they need the isolation transformer or when they need the isolation transformer. What's the deal with the frickin' isolation transformer? Remember, that's the one with the 1-to-1 turns ratio. You put in, whatever you put in comes out the same. So here is the bridge rectifier. Notice that the negative side of the bridge rectifier is grounded. So that's the Euro or Italian, I guess, ground symbol right there. So the negative side of that is grounded. Here's the hot side of the AC power coming in, and it goes through the fuse and goes to the bridge rectifier. This is the neutral side of the AC power, which is connected to earth ground. The neutral is also connected to earth ground way back at the circuit breaker panel, wherever it is. Those two are connected in one and the same. If I were to connect this directly to the AC power without an isolation transformer, since neutral and ground are connected together, they short out this diode. This diode is eliminated. It's gone completely. It's now a wire. It's a wire that goes all the way to the circuit breaker and all the way back again, but it is a wire right now. So what happens is that when this side is positive and this side is negative, remember we've got the AC, the sine wave like that. When this side is positive and this side is negative, the current will flow right through that diode. It's not supposed to be able to, right? Because it should be reverse biased, but we now bypass that diode, and it'll go right through this diode and right back to the hot side and blow that diode up. It'll blow the diode up because it's like putting a diode right across the AC power line. It's the equivalent of doing this. Here's the AC power, the mains. It's the equivalent of doing that. Well, what the hell? It'll survive when the current tries to go that way. Nothing will happen. But as soon as the polarity reverses and the current tries to flow that way, it flows right through the diode, drawing infinite current through it because there's no resistance there to speak of, and it just blows the diode up, and it'll also vaporize the traces right off the board. Like this whole neutral trace here will just vaporize. It doesn't even melt and curl up or anything. It's just gone. It's turned into copper vapor. It's just completely gone. And it has now blown that diode. It has now shorted that diode. So anyway, so that's the deal. The purpose of that isolation transformer is to remove the connection between ground and the neutral, so that what we're feeding this thing with is just the secondary of the isolation transformer, but it's not related to ground in any way. Then we can safely attach the actual the earth ground that is connected to the ground itself somewhere, to the frame, and then we have like a nice safe situation where nobody can get shocked and we're not blowing anything up. But if you tried to power this thing up directly without the isolation transformer and you grounded it, it would blow that up. Now, I routinely operate monitors without isolation transformers when I'm doing this lecture. I routinely take one that is supposed to have an isolation transformer and plug it right into the AC power. I am being extremely careful to not ever ground the frame. That's where the problem lies. And you can do something really stupid, and I have done this really stupid thing. Some soldering irons, if it has a 3-pin plug on it, the tip will be grounded. And I've had the monitor on my desk. I'm doing some kind of a demonstration, and I accidentally go, like that. Like I hit the cord, and it does that. Smoke and flames ensue. I've now blown a diode. I've tripped a circuit breaker. It's a disaster. I used to travel with a suitcase full of isolation transformers. I used to do this class like in Chicago once a year. And one of my suitcases was, and you could have 70 pounds at that time, was just filled with isolation transformers. And finally, I just figured out, look, in the classroom situation, we can power it up safely because as long as we are not grounded and touching anything, or we don't ground the metal frame, it survives. I don't really care if the frame has a bunch of voltage on it. If I'm not touching it and I am not grounded at the same time myself, I won't get a shock. I can touch a hot chassis. If I'm not grounded anywhere, no current will flow through me. And that's safe. But if I do something stupid and ground it, then it blows stuff up. So, you really need to have an isolation transformer on the thing. It would be stupid not to. So, Angel, how they get away with it sometimes, I don't know. It is either a monitor that has a switch mode power supply, and it really, which we're getting into right now, which doesn't really need an isolation transformer, or they're gambling and taking a 50-50 chance that it's connected right, and if it's connected wrong, it'll blow up the printed. You can run 120 volts right into the printed circuit board if you have it all hooked up wrong, because it'll look for that to be ground, and it'll go whoa through the printed circuit board. So I really don't know, exactly what they're doing. I'm guessing they're pulling out the transformer because, as we are about to see, the switch mode power supply does not require an isolation transformer. Hey, quiet out there. Okay. So anyway, this is a linear power supply, also known as a conventional power supply. And this is what's in all of our older monitors. Tomorrow, when we're looking at monitors, we'll take a peek at some of these things, but you'll see they're all just the same. They're all the same, which is nice. In monitors, there's some kind of standard designs that you see over and over and over again, and once you understand how they work, you can fix any monitor. I'm not saying it's easy, but I'm saying it's possible. I mean, I like monitor repair because I can really produce. I can fix them real fast. But I also like monitor repair because if I get an interesting failure, it's like detective work. It's like, ooh, what's wrong with you? What are you doing there? Let me find your bad parts and fix you. And I like that. I like working on monitors a great deal. I'm really kind of sorry to have seen them go, honestly. I mean, they are big and heavy and dirty. There are some downsides to them. But the way they work, and you'll see this tomorrow, is just fascinating. I'm really amazed that they got the damn thing to work at all, really. So anyway, that's linear power supplies. And in your world, you'll see lots of low voltage linear power supplies that make the 5-volt power supplies for games, 12-volt power supplies, and you'll see them in lots and lots of old monitors. So there's a newer, much better, really, and actually way more complicated but easier to fix kind of a power supply. And it's called a switched mode power supply. Since we're talking about monitors, I'll just stick with SMPS, a switched mode power supply. SMPS, switched mode power supply. And it works in really a completely different way. I mean, it really works in a way different way. So gird your grid, because here we go. I mean, here's the switch mode power supply. I guess I should ask you to relax a little bit in that when I'm done with my description of this thing, I will point out the stuff that fails all the time and how easy it is to actually fix most power supplies. Most switch mode power supplies. It's really pretty simple. So in the switch mode power supply, the mains, the AC power comes in, goes through a fuse, not a common fit, not a common to see a blown fuse in a switch mode power supply. Happens sometimes, it's just not very common. And the first thing that it goes to after the fuse is the bridge rectifier. So again, the bridge rectifier can be 4 individual diodes, or it can be a single one-piece bridge rectifier. So that's what these 4 diodes are. The AC power comes in through this standard connector. It's actually, this connector has a name. It's called an IEC, I think it's a 13, International Electrotechnical Committee or something like that. It's kind of a standard AC power connector that we use. At least, well, we use it worldwide. You've seen this in Europe, haven't you? Yeah, I'm sure it's common. So that's obviously where the mains is connected, the AC power. And the first thing it does is goes through a fuse and then gets to them, those 4 diodes right there, 4 individual diodes forming the bridge rectifier. Notice no transformer. If you remember the other power supply, we used the transformer first to change the voltage, and then we rectified it. But in the switch mode power supply, the first thing that happens is the mains, whatever it happens to be, goes into this thing and into the bridge rectifier. Let's ground the negative lead. Here's the positive lead of the bridge rectifier. And remember, this voltage is going to be pretty high. When we put the filter capacitor on it, the filter capacitor is going to keep the voltage at the peak. And in my world, again, this is around 165 volts DC. In your world, it's twice that. This will be like 320 volts DC, 340 volts DC. That's why you'll see that the filter capacitor is always a real high voltage capacitor. The main filter capacitor is typically like a 400 volt capacitor. Yeah, it is in this case.
But the same is for the diodes.
Yes.
High
So-
capacity, high, because there's no transformer. There's no transformer yet, so the diodes
Are receiving 165, 175
Yeah.
volts. Yeah, right. So where I live, this main filter capacitor here will have maybe 165 volts on it when it's working. In your case, it's 320, so be really careful. Be like really super careful here. In a power supply, it is possible that that capacitor might remain fully charged, even after you've unplugged it. It really shouldn't, not in a properly designed power supply. In a properly designed power supply, across the capacitor, electrically speaking, there will be a resistor of very high value, typically 1 megohm or so. And this resistor has a name. It's called the bleeder. It's called the bleeder resistor. And the purpose of the bleeder resistor is to bleed the charge off the capacitor after you unplug it. I'm sure you've seen plenty of times where it says, unplug this thing, wait 15 seconds, plug it back in, which fixes a lot of stuff. And what they're waiting for there is for the bleeder resistor to discharge the capacitor and then just kind of start all over again. But you're not sure of that. You're never quite sure of that. When you start working on a switch mode power supply, especially if you've never seen it before, you don't know if it even has a bleeder resistor, and you don't know if it's hooked up or good or anything. So it's entirely possible that the main filter capacitor might remain fully charged, and it will shock the heck out of you. So I always make a point of discharging the capacitor. Before I start working on something, I'll unplug it. Of course, I don't do this with the power on, but I'll just find the two little dots that are the capacitor and just short across them. I'm not like randomly coupling 165 volts into everything. I'm just finding the two leads on the bottom of the capacitor and shorting them to each other. Naturally, if it's charged, you'll hear a spark, you'll see a spark, and that will discharge it. What the problem comes when people don't realize that it has a bleeder resistor in it. So they carefully try to discharge it and it doesn't make a spark. And they're like, well, is it discharged or not? I don't know, man. I never heard no spark. I ain't going to touch that thing. It might be hot. You know, but you're technicians now. You know how to use a meter. All you have to do with the power off is check the voltage across the capacitor. If it's 0, it's discharged, right? If it's not, it's not discharged. And that, by the way, is a trick that I use sometimes. There's a few little tricks that can save you a lot of time. In a switched mode power supply, there are times like if there's no output from the power supply at all, I really want to know, do I have the input to the rest of the circuit that you're about to see? One quick and easy way to do that is to measure ever so carefully with the power on. Measure the voltage across the primary filter capacitor. Just find the biggest high voltage capacitor in the power supply and carefully, with the power turned on, measure across the capacitor. I don't care which lead goes where, which really, I'm just looking for the voltage. And see if it's there. If it is there, it means that everything over here is good, that the AC power is coming in, getting through the fuse and all that kind of stuff. In a switched mode power supply, the AC power comes, the first active thing it hits is a bridge rectifier. But I want to point out to you a circuit that it goes through first that is a 0 failure item. What I'm about to show you doesn't fail. I'm showing it to you because I don't want you scratching your head going, what's that? I don't even know what that is. The AC power comes in, and the first thing it gets to is something called a line filter, L-I-N-E, line filter. We refer to the mains as the line, the AC power line. That's our actual technical term for it. What you call the mains is the AC power line. So before it gets to that, it goes through a circuit that's a combination of capacitors and coils. So this coil here looks a lot like a transformer, but it's not. I'm going to show you on the board in just a second. And these square things are capacitors. They are not aluminum electrolytic capacitors, pretty obviously that they're not. They are polypropylene or polystyrene capacitors. Don't worry about them because there's 0 failure items. They're not wet inside. They really just don't fail. They're very low microfarads, like 0.1 microfarads or something. I'm showing you this circuit only to tell you that it doesn't fail and you never have to worry about it. But that circuit is called a line filter. So the way it's really hooked up is that the AC power comes in, goes through a fuse, F1, and the first thing it really goes through is a circuit that consists of a coil thing, technically known as an inductor or a choke. This coil, it looks like a transformer turned sideways. It's not, but this coil is, technically all coils are inductors. They're called inductors because they induce voltage, and you don't really care about that. So we have resistors, capacitors, and inductors. Coils really don't fail. I mean, pinball coils do, but not like electronics. They don't really fail. And there are some capacitors here. And these are the yellow ones I just showed you. Sometimes they're not yellow. Sometimes they're green or blue or something like that. They're very small voltage. Small microfarads. So like 0.1 microfarad. And they are not polarized. There's no plus and minus. There couldn't be because we have AC coming in, right? So a capacitor can't be polarized on AC. Half the time the polarity is incorrect. Right? And then a couple of other capacitors here. And these are the other ones that I see. And sometimes there's a couple of little ceramic disc capacitors. You use these in your kit. These are little capacitors. Again, they're called ceramic disc capacitors. No, very low microfarads, like 0.1. No, they're not wet inside or anything like that. So whatever the mains voltage is, I'll use yours. 240 volts AC comes in. 240 volts AC comes out. So it doesn't change the voltage at all. So this filter is called a line filter. It's called a line filter, and line, again, AC power line, the mains, right? So here's the deal. This is called a switch mode power supply, switching power supply. There's something in there that's switching on and off, and it's switching on and off real fast. It's a MOSFET. It's switching on and off 50,000 times a second. And every time it switches on and off, as a natural byproduct of the way it works, it generates a crap ton of electrical noise, electrical interference. Not noise that you can hear with your ear, but electrical noise, kind of like static. This noise is known as EMI. It's electromagnetic interference. So switch mode power supplies, just by their very nature, are switching on and off, and they're like little radio transmitters. They generate a crap ton of this EMI. We cannot allow the EMI to escape the power supply. If this electrical noise generated by the switch mode power supply gets out, it can get into like the monitor. And you'll see all kinds of weird diagonal lines and dots floating on the monitor. It can get into the computer and cause the computer to reset or never boot up at all. It can make all kinds of weird sounds. It's bad mojo. So we don't want that EMI to escape the power supply, so we have this thing called the line filter. These parts, capacitors and coils, have very interesting electronic properties. You don't have to know this. You don't have to know this. Won't help you fix anything, but here you go. They have an interesting property. For example, capacitors will pass alternating current right through it like it's invisible, but it will block direct current. A capacitor blocks DC but passes AC. And the higher the frequency of AC, the easier it goes through a capacitor. To a low frequency, a capacitor has a lot of resistance. To a high frequency, the capacitor becomes invisible. Well, the EMI is super high frequency. The EMI is 50,000 cycles per second, let's say 50 kilohertz or so. The AC power coming in, remember, is only 50 hertz, 50 cycles per second, super low frequency. So the line filter, remember the rest of the power supply is here. The line filter consists of coils of capacitors. These capacitors here are grounded to earth ground. It's one of the reasons why it's a good idea to have an earth ground, because they are the things that remove the EMI. The 50 hertz mains goes right through and powers the power supply. But the super high frequency EMI that's trying to escape gets sucked up by these capacitors and gets shunted, gets sent to ground to remove it. So it's a way that we can pull off the EMI without affecting the 60 cycles that we need, or 50 hertz that we need to come in and power the thing. There's also this inductor, which is also known as a choke. An inductor in this case is also known as a choke, because an inductor will pass DC right through it like it's invisible. It's just a wire. So the DC goes right through it, but it will block AC. And the higher the frequency, the more it blocks it. So this coil allows the AC to come through, but if any EMI tries to escape, it blocks it and can't get past it. And then finally, if anything does escape, this 0.1 microfarad here basically shorts it out. This 0.1 microfarad is invisible to 50 hertz. The 50 hertz power can't even see it. But if there's any bit of 50 kilohertz EMI, that looks like a dead short. It just looks like a dead short to EMI, and it shorts it out. So, but the deal is that this circuit, this line filter circuit, is super duper reliable. Something physically might break it. You might see physically a broken wire or something, but in terms of electrical failure, it doesn't fail. So getting back to this deal, but the point that I'm making here is this, that the way it works is the AC power comes in through a fuse, goes to a bridge rectifier, which we should be pretty familiar with now. That changes it to DC. If I measure the voltage across my filter capacitor, which we now refer to, by the way, as the primary filter capacitor, you'll see why in just a second. There's some other capacitors. This is called the primary filter capacitor. If I measure the voltage across that capacitor and find that it's good, 160 or 320 in your case it might be, I have actually tested all of these parts, haven't I? The capacitor is good, the bridge rectifier is good, the fuse is good, the line filter, consisting of all those things that I just showed you, between the AC power and the bridge rectifier, all of that stuff is good. Is everybody with me on the concept there? I'm trying to do stuff fast and accurately. If I can come up with a quick shortcut where I can test a whole bunch of parts by making one measurement and see that they're good, I'm going to do that. So again, with the power turned on, I carefully turn the power supply over, carefully measure the voltage across the primary filter capacitor, and if it's there, I know that everything here is good. I don't have to test the fuse separately. I don't have to test the bridge rectifier. Does all that make sense to everybody? You know, I want to do this quickly. I got things to do. I don't want to mess around with this stuff. No. But you can also use this technique to check if the filter capacitor is staying charged after you've unplugged it. Unplug it, measure the voltage across the filter capacitor, and you can watch it discharge. If you hook up a meter to it and then turn it off, you can watch the capacitor discharge. The voltage goes lower and lower and lower. Anyway, so at this point, we have, let me use my voltages because I'm familiar, I don't want to make a mistake. So at this point we have plus 165, let's say, volts DC. Well, if you remember in the previous power supply, the linear power supply, if we're going to change the voltage, we do that first. We change the voltage, and we did that with a transformer. So now it's time for the transformer. We have made a DC voltage here, but it's way too high. Let's say we want 12 volts out of this thing, or 5 volts or something. So it's way too high. So now we connect it to our transformer. So there's the primary winding of the transformer. Here's the core of the transformer. And technically speaking, this core is a different material. The core, these yellow transformers, the core in the yellow transformer is not iron core. It's of a material known as ferrite. The transformer core is ferrite, F-E-R-R-I-T-E, ferrite. Ferrite is a mixture of iron and ceramic. Ferrite is like, we call them refrigerator magnets. This is ferrite. This is what ferrite is. I'd like to continue to own these magnets. Oh, sorry, you're going to have to fondle that and pass it back. So imagine taking a bunch of finely powdered iron filings, mixing it with clay slurry, and baking it in a kiln like a china plate. That's what ferrite is. We have lots of ferrite core things. And the transformer in the switch mode power supply is a ferrite core transformer, which technically is supposed to be shown with a dashed line like this. A ferrite core is supposed to be dashed like that. It isn't. On lots of schematics I see they just draw on the core, but technically 2 solid lines is an iron core and 2 dashed lines is the ferrite core. And then we have some kind of secondary windings here. So the ferrite core transformer is used for high frequencies. The iron core transformer is for a transformer you're going to plug into the wall. 50 hertz, 60 hertz. The highest it would even be was 400 hertz for a power transformer, but we don't use it. So 50 hertz or 60 hertz. But a ferrite core is required when we can use it when the frequency is high enough. If the frequency is high, many thousands of hertz, in this case 50 kilohertz, we can use this ferrite core transformer, which is one of the reasons why we now have switch mode power supplies everywhere. They're a lot less expensive. If you remember, if you're old enough to remember the original wall wart, as we called it, the original power supplies that you plugged into the wall, they were real heavy, weren't they? They were big and heavy and inefficient. They got really, really warm. And those had iron core transformers in them. The ferrite core transformer just slaps together. It's really inexpensive. A ferrite core transformer might be 50 cents or $1, and that same transformer as an iron core transformer that would do the same thing would be like $10. The iron core transformer or more. The iron core transformer, to make it, they first wind the bobbin, the coil, but then they have to laboriously assemble those flat E's and C's that I talked about, the flat iron laminates. They have to kind of laboriously assemble that into the core. There's no way to wind it around the core because the core goes through the center of it. And then they have to clamp it and glue it, and it's like so these things, these entire power supplies cost less than just the giant transformer that you see in the bottom of an Atari game, or the two transformers that you see in the bottom of Pac-Man. This power supply, this entire power supply, costs less than just the transformer cost for those older power supplies. So one of the reasons they have this kind of switch mode power supply is cost. They were originally developed for spacecraft. They were originally developed for like space probes and satellites and stuff like that. You don't want to be launching an iron core transformer into space. I mean, they're really, really heavy. It's $10,000 a pound to launch something. So they developed the switch mode power supply that powers Voyager and all of these, all the Mars probe, everything like that that goes out into space was made with these ferrite core transformers because they're so light. It used to be like $100,000 a watt. Like it would cost $500,000 for a power supply, a switch mode power supply. Now they're just disposable. They're $25, $50. The miracle of modern electronics. Anyway, so let's say we want to make a power supply with multiple outputs. It's certainly possible. In fact, most power supplies have multiple outputs. A single output power supply is not as common as multiple outputs. Since we need multiple voltages for things, why not make one power supply that makes a bunch of different voltages? So, like one of these windings might be like a center tap winding that will eventually make the 5 volts. One of these windings might be the 12 volt winding. One of these windings might be the isolation winding. This might be an isolation winding. Sorry, no, wrong power supply. Sorry, this might be a 24 volt power supply. We can hang as many secondaries on the primary and the core as we want. But remember that the output of a transformer, what is it? AC or DC? AC, right? So wait a minute, we need DC. So even though we've already made DC once, somehow magically after it got out of the transformer, it magically turned into AC again. The transformer itself didn't do that. Transformers can't change DC into AC, but we'll find out how that happens. But the output is AC. So even though we've rectified it once and then lowered the voltage, let's say, with the transformer, we have to rectify it again. And this is where our high-speed diodes come into play. So you might see, for example, a center tap winding with 2 high-speed diodes connected to it. So these are 2 diodes with their cathodes tied together. We talked about this before, making a full-wave center tap power supply. And this is the dual diode assembly that I showed you before. This is the dual diodes that's what these guys are. It's the thingy I showed you before that is two high-speed diodes all connected together in one package, like that. So we might have two diodes making a power supply, or in the switch mode power supply, it's very, very common to see one diode here. We know that we can make a power supply with one diode, right? Remember that was a half-wave supply where we got a pulse, and then it waited, and we got a pulse, and then it waited, a pulse, and then it waited. And when we started out the discussion of linear power supplies, I was saying like, whoa, look, we're missing half the time there. There's no pulse right here. Ooh, it's not very efficient. But this thing is working at 50 kilohertz. This is operating at an extremely fast speed. So even though this is going to be missing half the pulses, I don't really care because I have so many freaking pulses. The pulses aren't coming along like this. They're coming along like this. There's 50,000 of them every second. And so what if I'm missing half of them? The next one's coming down the pike a 50,000th of a second later. It's like filling a bucket full of water. You know, once it's full, do we care how fast the stuff's coming in? No, it's just going to overflow. I mean, I have plenty of extra pulses, and so a half-wave supply is perfectly okay. So it's very common to see just one high-speed diode. And it may look like a regular diode, or it may be in a package like the TO220 package, like this. In most of like our smaller box power, switch mode power supplies, they're just diodes. They're just 3 amp size diodes or 1 amp size diodes. But they're what they call fast recovery or high speed diodes. You might see a part number like FR104. It's a fast recovery diode, as it's called. High speed diodes are sometimes referred to as fast recovery diodes. So you do have to use high speed diodes. And they are sometimes failure. Output diodes on power supplies, these are the output diodes, fail sometimes. And you cannot use like the diodes I gave you, those are conventional diodes. You can't use those. You really have to get the right replacement. Google it and find it, high-speed diode. So what comes after the rectification? Filter capacitor. So after the diodes, there is a filter capacitor. And these are your number one problem. This is Ichiban problem, number one problem. The filter capacitors. So these capacitors, the filter capacitors, are called the output filter capacitors. I'll show you in just a second. So these capacitors are they're called the output filter capacitors. They're called the output filter capacitors, and this is the number one problem on the planet Earth. It's easy to tell which are the output filter capacitors. Go ahead. The output filter capacitors are always all together at one edge of the board, right by wherever the output connector, in this case it's that connector right there. Inputs are on the left, there's AC power coming in, outputs are on the right, and there are the output filter capacitors. So what you're looking at is, there's the transformer. In this case, the diodes are these guys mounted on the heatsink that look like transistors, but they're not. And then these output filter capacitors. And these are the ones that you often see are bulged or leaky. They are the number one problem in power supplies everywhere, bad output filter capacitors. And there's a reason for that, and you should know this reason. Wake up, wake up. It's the high operating frequency. Over here we have the primary side. This is the primary side of the power supply. Remember, that's called the primary winding. So this whole side of the power supply is the primary side. And it's really operating where I live at 60 hertz, where you live obviously 50 hertz. That's very, very slow. And the capacitor can really handle that pretty well. There's current flowing into the capacitor, it's flowing out of the capacitor, it's only 50 hertz. But over here on this side, the current flowing in and out, in and out, in and out of the capacitor at 50 kilohertz. We refer to that as the ripple frequency. The ripple frequency over here is only 50 hertz, or 60 where I live. The ripple frequency over here is 30, 40, 50 kilohertz, and it gobbles up capacitors. That's what really eats up capacitors, is high frequency. And you can imagine that this is true. I mean, I used the analogy of your automobile before. You know, if you drive your automobile carefully at very low RPMs, the engine will really last a long time. Can you drive your car super fast and have the engine really revving high? Yeah, you can. It's the most fun. But will it eat up the engine faster? Of course it will. So same thing here. So high frequency operation, once you identify how it works and you can see, oh, this capacitor is dealing with high frequencies, it's not surprising if that's the capacitor that fails. They bulge on the top, they leak out the bottom, or they just go bad. Their ESR climbs and climbs and climbs, but very often they bulge. The output filter capacitors are very often visually bad. The top is shrunken back, it's exposing the top is domed on the top, the bottom is pooching out of the bottom, that rubber plug that comes out, you know, all that stuff happens because it's operating in a real high frequency. So these things are common failures. Now, because of this high operating frequency, capacitor alone may not be enough filtering. You may see some additional filtering on a power supply. Let me see if I can see if I'm actually. Oh, that's linear. On the power supply right here, there's a coil. It's covered with heat shrinkable tubing. This is a coil. I can tell it's a coil because it says L on the board, if I can get the camera to see it here. If you look right up here, it says, you probably can't see it, it says L801 on the top. Remember, coils are labeled with an L, standing for this dead dude named Lenz, L-E-N-Z. Carl Lenz, I think. I don't know, it could be Fred Lenz. I don't really know. Lenz. Anyway, so that's a ferrite core coil. You see an inductor. You can see the ferrite core. You see the grayish-black substance. That's the ferrite core. And it's just some wraps of wire around it. It's not a failure item. But remember I mentioned that coils have an interesting property where they will pass DC but block AC. And the higher the frequency, the more they block the AC. So the coil goes here. The coil, which is also known as a choke. This coil acts like a filter. It's also referred to as a choke because it literally chokes off the high frequency but just lets the DC through. And in some cases, many cases, you will see a capacitor, the coil, the choke, the coil, and yet another capacitor. It's very common to have two capacitors here. Not always. Sometimes they just have one capacitor. Sometimes they don't even have a choke. But usually it's a capacitor and a choke, and sometimes a capacitor, a choke, and another capacitor. And now we're done. The outputs are like plus 5 volts DC, maybe plus 12 volts DC, maybe plus 24 volt, whatever, whatever voltages we actually need. Notice no further regulation is required. Ooh, that's interesting. If you remember the linear power supply, we turned it into DC, we filtered it, and then we hung a voltage regulator on the output, either a 3-terminal regulator or a series pass regulator transistor and its circuitry that drives it. Something's over there. But in this case, it comes out perfect. It comes out perfect as 5 volts or 12 volts or 24 volts or, whatever, whatever it's supposed to be. So the big question is, how did that happen? We were DC over here, but we ran it through the transformer, and it became AC again. So we had to rectify it again with these high-speed diodes and filter it again with this filter capacitors and maybe a coil or something like that. You know, how did that happen? And when we started the discussion of transformers, I kind of mentioned that a transformer is really an AC device. It's really, you know, the output's always AC. I also mentioned that we put AC into the transformer, but I did mention that the magnetic field just simply has to move. It doesn't have to be AC necessarily changing polarity. It just has to be able to build up and collapse. So the way it works is that we have one side of the ferrite core transformer, the power transformer, connected to whatever that voltage, whatever you want to call that. The other side is connected to our buddy, the MOSFET. And it's always an N-channel MOSFET. Always, always, always. And remember, this is called the drain. This is called the source, sorry. This is called the source. This is called the source. This one over here is called the drain. And remember, the controlling element is called the gate. It's called the gate. And the gate is connected to some kind of circuitry, either an integrated circuit or some kind of circuitry. And this thing is known as the PWM controller. This is called the PWM controller. And remember, I said it takes like around 5 volts to operate the gate of the MOSFET. In reality, about 3.6 or 3.8 or something. But we give it 5 volts, and this is where it gets it. It gets it from some circuitry or an integrated circuit called the PWM controller. I really wonder where my other power supply is. Give me 1 second. I'm just missing this sample power supply, which I'm pretty sure I got. I just don't know where it is. I really want to show this.
And there's also a PWM by the handtracks.
Say again?
There's also a PWM on the handtracks on the left side.
PWM? What are you talking about?
The power control. Called a small strip in there.
Not this one. This is a linear power.
Yeah, no, but there's also one that controls very fast switching.
I'm not sure what you're talking about. Oh, there it is. I'm sorry, my bad. Okay. All right. Let's start the class all over again. So here's an example, for example, of the back capacitors. It's real common. These are the output filter capacitors. I can tell that because there's the output connector, and they're all together. They're all the low voltage capacitors all together, and you can see how these capacitors are domed, can't you? It's pretty easy to see even from your perspective here on camera that those are domed on the top. Those are the output filter caps, and there's the coil I was talking about, and you can clearly see the ferrite core, the ferrite rod that's in the center of the this guy right there. So on this guy, let me see, where's the output diode on this one? Yeah, it's just mounted on the heatsink. So on this one, let's take a look at this. Here's the MOSFET mounted on the heatsink. The MOSFET will always be mounted on the heatsink. There's the MOSFET, and there's the little integrated circuit that drives it. It's just a little 8-pin dual inline package integrated circuit, just like the one you used on your first. Looks like the one you used on your first kit. It is not the same IC. It just is the same package. You know, again, you have to be careful. Never look at something and say, "Oh, it's this," until you look at the part number on it. So this chip is the thing that goes right to the gate of the MOSFET. So the source of the MOSFET is grounded. The drain is connected to the primary winding of the transformer, and it's controlled by this device, which is called the PWM controller. So here's the way it works, and it's pretty damned interesting. When the transistor is off, there is no current flowing through the primary winding, obviously, if the MOSFET is turned off, N-channel MOSFET, nothing's happening. When we want to get an output from the power supply, the PWM controller turns on the MOSFET. When the MOSFET is turned on, that 165 volt power supply travels through the primary winding, through the MOSFET between the drain and the source, which is now like a switch, right? The closed switch that is conducting to ground. That builds up the magnetic field, which of course surrounds both the primary and the secondary, since they're wound on the same core. Then the transistor is turned off. The MOSFET is turned off. Here's where it's off. Here's where it's on. Here's where it's off. When it's off, the magnetic field collapses. And we get the output from the output side over there. So the magnetic field just has to move. It just has to build up and collapse. It doesn't have to reverse polarity. It just has to build up and collapse. And that's how we get the transformer to have an output, a nice AC output. We haven't put AC on the input. We put DC on the input, but we have chopped it up. We're turning it on and off. And wake up, here's the cool deal. Depending on how long we allow the MOSFET to remain energized versus not energized, the bigger the magnetic field will be, and the higher the output voltage will be. This is how we regulate the output voltage. We don't just make a voltage and then cut it down like we did before. That's also inefficient and wasteful. Instead, we never make 1/1000th of a volt more than we actually need. This integrated circuit turns the MOSFET on and off at 50 kilohertz, but the longer it's allowed to remain on, the bigger the magnetic field is. If it's only allowed to remain on for a short time, the magnetic field is smaller. By changing the magnetic field, we change the output voltage. So here's what I'm talking about. Pay attention, pay attention. It's really cool. It's easy to understand, but it's really cool. If I were to draw a graph of the on and off times of the MOSFET, let's say, when everything is working all right, it might look something like this, where here's where it's off, here's where it's on. Here's where it's off, here's where it's on. Here's where it's off, here's where it's on. And these are just the on and off times of the MOSFET. Right? So it appears to be on maybe 25% of the time, let's say, and it's off here for maybe 75% of the time. That is referred to as the duty cycle. We call this the duty cycle. D-U-T-Y-C-Y-C-L-E, the duty cycle. So this would be a 25% duty cycle. It's on for 25% of the time, it's off for 75% of the time. The longer it's on, the higher the output voltage will be, right? So let's say when everything is perfect, that's what it's doing, 25% duty cycle. Somehow or another, this chip, which is called the PWM controller, is sniffing the output. We'll see how that works in just a minute. Somehow this chip is always sniffing the output. We talked about this previously. Something has to tell the power supply what the output voltage is so it can compensate if it goes up or down. So it's always sniffing the output in a way that we'll find out shortly. And let's say for the sake of discussion that the output voltage was to drop for some reason. Like maybe the AC power, the mains dropped. Somehow magically the PWM controller sniffs that and says, wait a minute, buddy, your voltage is dropping. I'm going to make the pulses wider. Meaning, remember it's time in the horizontal direction. Meaning that the transistor is on for a longer period of time. That builds up a bigger magnetic field and pops the voltage back up to what it should be. Let's say, for example, that the voltage was too high, like maybe the AC power jumped up or something like that. Again, the PWM controller somehow smells that and says, whoa, brah, your voltage is too high. I'm going to cut back on your pulse width. I am going to modulate the pulse width. Changing the pulse width, right, like this, is known as modulation. Modulation is just a fancy word for change. When we are modulating something, we are changing it. So we're changing the time in this case. PWM happens to stand for pulse width modulation. Pulse width modulation. Pulse width modulation. Well, of course, when we're talking about pulse width, we're talking about time, aren't we? When we're modulating, we're changing the pulse width, we're changing the amount of time that the pulse is high or low, that the transistor is on or off. So it's called a PWM controller, and that's how we control the output. We don't need additional voltage regulation here because we never make anything that isn't correct. We never make any voltage that's too high and have to cut it down. It's not too low, it's not too high. It's always exactly what we want it to be. It's called PWM, and it's sort of the miracle of modern electronics and MOSFETs. Let me just give you an example. A real easy example of PWM to understand is a variable speed drill. So imagine you have a variable speed drill, and imagine it's a 12-volt drill with a 12-volt battery. If you didn't know better, you would think if you pull in the trigger halfway and it goes half speed, oh, I must be putting 6 volts on the battery. You're not. You're always putting 12-volt pulses on the battery. You are modulating the pulse width. Like
But Randy, I have one question, a short question, maybe stupid question, I don't know. A sine wave is coming in.
This is DC.
It rectifies.
Sine wave comes in, rectifies. We have DC.
Then it goes to the coil. It makes it AC again, and then the MOSFET is making it a pulse.
Making it pulse, correct.
On off.
Correct.
On off. So
right.
It makes it a pulse.
Yes.
A square wave.
Yeah. Well, it's not square unless it's 50% duty cycle. Hang on, I'm right there. Yeah, it's a good question. Let me finish my discussion. You'll see what I mean. The easiest way to understand how this works is think of a variable speed drill. So if you pull the drill in just the trigger just a little bit, sometimes you can hear it making a tone. That's the frequency of the pulse train. That's how fast it is, 700 hertz or whatever it happens to be. Let's say I pull in the trigger just 10%. So it's going real slowly. I'm not putting 1.2 volts on the motor. Remember, the battery's 12. If it's going 10% of the speed, I'm not putting 1.2 volts on the motor. I am putting a full 12-volt pulse on the motor. Remember, that's called the amplitude. A 12-volt pulse, but it's only 10% duty cycle. It's off for 90%. It's on for 10%. It's off for 90%, on for 10%, and the thing goes at 10% speed. I pull in the trigger a little more, 1/4 of the way. It's now traveling at a quarter speed. It's not 3 volts out of the 12 volts. It's a full 12-volt pulse, but it's 25% duty cycle. If I pull in the trigger halfway, I have what we call a square wave. That's a 50% duty cycle. 50% off, 50% on, the motor's turning at half speed. But it's a full 12-volt pulse. It's just 50% duty cycle. And like your meter is an averaging device, the motor is an averaging device. Almost all electronics does this kind of thing. If you give it a rapidly fluctuating series of pulses, it just averages them out. So the motor would go at half speed, and you keep pulling the trigger, and then obviously, eventually, you put the full 12 volts on the motor, and it's turning at full speed. But this is also how we dim LEDs, how we dim lights, and these days, you can have, even in your home light, you can have any color you want, you can make any brightness you want. Same thing with some of the newer machines down there, beautiful LEDs. Well, when you see an LED getting brighter and dimmer, if you didn't know better, you'd say, oh, putting more voltage on it, it's brighter. The lower voltage on it, it's dimmer. That is not how it works. It's PWM. If they want it to be bright, they use a wide pulse, a high duty cycle. If they want it to be dim, they narrow the pulse and give it a less duty cycle. But the pulse amplitude is the same. And in fact, if you look at pinball machines, are there any pinballs in this museum?
Yeah,
all been there?
We have the baby back as well.
Oh, okay.
That's pretty fun.
Really? You have baby?
Yeah.
You poor thing. I'm so sorry. I'm so sorry for you. Anyway, you can use let's say you have an LED that's designed to work off of 5 volts. It's got a resistor built in or whatever. It's a 5 volt LED. You can use a power supply that's a 20 volt power supply to power the LED. You just can't keep it on for very long. So at 2 or 3% duty cycle, the LED is really dim, and the most duty cycle you're going to put on it is 25%. As long as you keep the duty cycle down, you can use a higher voltage power supply than the LED can actually take. So it's called PWM, and you see it all over. It's how the Tesla car works. It's how Hassan's Volkswagen ID4 works. He has these motors, and they work off of like 600 volts or something like that to control the speed. There's a controller box. It's a PWM controller. When he barely hits the accelerator pedal, he's just putting a 10% duty cycle on it. It's still 600 volts or whatever it is. It's just a very low duty cycle. The more he presses down on the accelerator pedal, the wider the pulses get and the faster he goes. Man, that thing can accelerate.
Yes.
Like for a short period of time, he just demonstrated. He didn't even say, "Hey, Randy, hold on." It was just like, whoa, holy cow. It's just, it's so responsive. If you happen to see somebody in an electric wheelchair, same thing. That's how she controls the motor and stuff like that, is with the joystick. As the rider pushes the joystick forward more and more, the pulses get wider and wider and wider, and it increases the voltage. Not the voltage, increases the power of the motors. Make sense? So it's called PWM, pulse width modulation, and almost all motor speed control is done with PWM. Almost all. It's very unusual to know. So this is the basics of how this works. And so far, of all the things that I've shown you here, number one, by far, the thing that fails the most is the output filter capacitors, which again are very easy to locate. They're always on one end of the board, right by wherever the output connector is. You don't want to have the output filter capacitors here and have the output connector way the heck over there. That's dumb. You put the filter capacitor, the output filter, right where the power supply output is, and those are they. And in your case, they're always going to be the low voltage capacitors. Like these are 1,000 microfarads at 25 volts. They're always going to be the low voltage caps. The high voltage cap is the primary filter cap, and that is not anywhere near as common a failure. It hardly fails at all because it's only working on 50 hertz. The output filter capacitors are operating at 50 kilohertz, and that's what gobbles them. Does that make sense so far?
Yes.
Okay.
Yes.
So when we come back from this break, I'm going to answer the most amazing question of all. How does a bad capacitor cause the voltage to go too high? What the heck are you talking about there, Randy? You had asked that question before, right? So I'm going to answer that question. So let's take a quick break. Let's take 10, and then we'll finish.
What's the failure rate of the PWM controller I see?
Not very high at all. It's just not. It's just not a common failure. Not at all. Crashing and burning. You want another?
Yes.
It's a little late now, probably. I should have offered it to you earlier. I know. The other way around.
No, it's just too much of one, so I just can't.
My bad. I should have offered you this.
You know.
Well,
Oh yeah.
this probably is on the spec. Is that something that would buy on the website?
Well, I do offer for for sale on the website, but I'll give you a link. It's actually up for downloading right now, and you can download it. Just like drop this on your notes, and I'll leave it up there. It's my website, randyfrom.com.
Put it in the stream as well.
Slash EDD. Stands for Big Blue. And it's there at the moment temporarily because I needed it to be there. But if you go there, I don't think you can download this on your phone. It's 145 megabytes.
That's also not good.
Maybe send the link to your dad and have him download it on there. The green book's on there too.
Normally it's till 4, but yeah. It's 3 o'clock right now. Yeah, sorry.
I don't,
So you can take a breath outside, fresh air.
Ooh.
Nobody's explaining that to me. Nobody's explaining to me. There's this whole tirade about grounding or something like that. It's exploding and something. Yeah, there was not enough information there. There was not enough information. But I'm saying, it needs to stop so that these things can be addressed. Yeah, I just can't.
question. Sorry, my question,
yes.
Randy. My question. I have a question. Because I'm missing something, I guess. The adapters, the power supplies for your phone or for your laptop, or I can put it in 230 volts AC plug, but also in the States.
What the
In
same
a-
thing?
in a one-
Well, this and mine as well are now working on the 240. So this is the one.
Is this what this power supply can do?
Yes, and that's one of the beauties of the switch mode power supply is that in the old days, if manufacturers made power supplies, they'd have to make half a warehouse full of power supplies for Europe or UK, and half of a warehouse full of power supplies for the United States of America, and they couldn't interchange them. But by using this system, the PWM controller simply modulates it to what it should be. In other words, if in the United States it was 25% duty cycle, and I take the same thing and plug it in here to get the same voltage out, it would be a 12.5% duty cycle. Since the input's twice the voltage, it would just cut the PWM down to what it needed. So that's the beauty of these. If you look at any modern switch mode power supplies, it says it works on anything from 100 volts, which is Japan, up to 240 volts. They all say that. Some say it's good to 90 volts, just by adjusting the pulse width.
Nice. Thanks
Yeah.
for eye opener.
It's beautiful, yeah. It's really great. So the deal is, though, that something has to tell the PWM controller circuitry what's going on the output so that it can correct it if possible, if it needs to, which it does. And so that's done with an input into the integrated circuit or the circuitry known as the voltage reference. It's a voltage reference input that goes into the integrated circuit. All we have to do is feed some of the output back into this voltage reference input, and it'll know what the output voltage is. Well, think about this for just a second. Put on your thinking cap. I know it's late. I know you're weary. I know your plans don't include me. But here's the deal. These three output windings, the voltages will all track each other, won't they? If you think about it, they're all just windings on the same transformer, the same magnetic core. If one of these windings goes up 10%, they all go up 10%. If one goes down 5%, they all go down 5%. So in order to tell what the output voltage is, we just have to pick one of the outputs in a multiple output situation and look at it. If I make it perfect, the other ones will all be okie dokie. So let's say we pick the 12 volt output, which is common in a multiple output situation that they use the 12 volt output. So all we have to do is connect that back into the input, and it'll know what the output voltage is. However, wake up. You may have noticed, you probably didn't, that on the primary side of the power supply, I used the earth ground symbol. And on the secondary side, this is chassis ground, if you remember. If you did your homework, you learned about ground. It's chassis ground. The chassis ground is a common 0 volt point for all the circuitry, but it is not hooked up to the earth itself. On this side, it is hooked up to the earth itself. We talked a little bit about this previously. In a switch mode power supply, nothing from this side, the secondary side, can touch anything on the primary side. Nothing, not one single thing on this side can touch anything on this side. They are completely isolated. So in this case, this is where our isolation comes from. We have to have isolation or things blow up. In this case, we don't use a one-to-one isolation transformer. Almost all transformers have this property referred to as isolation, where the primary winding is not galvanically, electrically touching the secondary. There's a million, billion, zillion ohms between them. It is only magnetically talking to each other. Right? So if anything from that side touches this side, we're in trouble. It's going to be smoke and flames and stuff like that. So what you would think you could do is take this 12-volt output and run it right back into the input. But you can't do that because you can't touch those two sides together. So instead, there are two different ways that we do this. Let me make the MOSFET just a little smaller to give you some more room. There are a couple of different ways to do it, and one way is to put yet another winding on the power transformer. This is a secondary. It is an output, but I've drawn it on the left side, which you know is where the primary lives. Normally inputs are on the left, outputs are on the right, but this is a secondary winding. It's an output winding, but I'm drawing it it is drawn on the left-hand side because it is going to feed this thing, as you're going to see in just 1 second. So if I put it on the right hand over here, I would have to make a wire going from here to here to here to here to here, and it would look bizarre. Plus, it has a different ground, so they don't do it that way. So I'll draw it here. And let's just call this a 12-volt winding. In other words, it has the exact same number of coils as that 12-volt winding. Is everybody with me? Exact same number of turns. It's the same secondary, way less current, finer wire, but the same number of turns. And this one we're going to ground with the regular earth ground, just like everything on the primary is connected to the earth ground. Well, we're going to use this as a reference. We're going to use this as a voltage reference. In other words, if I can measure this and find it to be 12 volts, I know that that's 12 volts. If this is 11 volts, I know that this voltage has dropped. It's 11 volts. Everybody okay on that, right? But the output here is AC. It's not really a sine wave, but it is a sine wave. But it's AC, and that's a lousy reference. You can't make a voltage reference out of AC. It's always changing, so it's useless as a reference. Let's turn it into DC. So we use a diode, and this is a high-speed diode because all this stuff is operating at 50 kilohertz. Well, after the diode, what comes in a power supply after the diode is a capacitor. So we have a capacitor here, like that. And then this becomes our voltage reference. In other words, we've made a DC power supply just like this, but it isn't really a power supply. It's not powering anything. It is simply making a reference voltage that we can use for the chip to know what's going on out here. Everybody with me on the concept so far, right? So when everything is good, that's 12 volts. That's 12 volts. This thing knows it's 12 volts, and it gives us whatever the duty cycle is that we need to get 12 volts out. If the output voltage drops here, it's also going to be dropping here, and it senses that and makes the pulses wider. And if it goes up too high, it makes the pulses narrower. Now, it's not really going up and down. Remember, I mean, that's the opposite of what we want to do, right? If we're going to regulate a voltage, we don't want the voltage to go up and down. Oh, you're too high, I'll bring you down. You're too low, I'll bring you up. It stays steady because it's doing this 50,000 times a second. At 50 kilohertz, 50,000 times a second, this chip is sniffing the output via the sample circuit that it's just made. And if it is low, 1/50,000th of a second later, it's going to make the pulses wider and bring it back up to what it should be. So it doesn't really vary at all. It just stays exactly rock solid on the output. Everybody with me so far? Capacitor failure is a big, giant deal. Capacitors that are working on high frequencies fail a lot. And this one is being driven at super high frequencies, 50 kilohertz. Well, because this power supply, this sample circuit we made doesn't have very much current drawn from it, that capacitor is really small. The output filter capacitors have to supply a lot of power. There's a lot of things dragging current out of them. So these are 1,000 microfarads, a couple of them connected in this circuit kind of equal 2,000 microfarads, or they're 2,200 microfarads, or 3,300 microfarads, or 6,600 microfarads, whatever it is, they're giant. But typically, this is an itty-bitty capacitor. This could be as low as 10 microfarads. It could be maybe 100 microfarads. I've seen a couple where it's 220 microfarads, but that's real low. Well, think about this for just a second. As this capacitor fails, bad capacitors do what? Bad capacitors cause low voltage. Thank you very much. So as this capacitor, as ESR increases, the voltage drops. Well, that's the voltage to the voltage reference. What does the chip think is happening over here? It thinks that that voltage is dropping. What's it going to do in response? It's going to make the pulses wider, and all of a sudden the output voltage here shoots through the roof.
Whoa, that's the problem.
That's the problem, because this itty-bitty, teeny-weeny little motherfucker right here has lost its marbles, and the voltage reference is what has dropped. But wait a minute, it gets worse, because now the output voltage is shot through the roof, and these capacitors are blowing up. They're all domed and blown up. So you go, oh, this is easy. I'm just going to replace the domed capacitors. And you replace all those guys, you plug it up, and boom, it happens again. It's like, something's blowing out these capacitors. I don't know what. So I mentioned this before. I'm going to mention it again right now.
Don't forget the small one.
There's a bunch of little small capacitors here. And you don't have to know what they're doing. You just have to see them. So, for example, there's this little guy right here. You know, do I specifically maybe know what it's for? Well, I probably do. It's probably that. But I could be wrong. I don't care. I have an ESR meter. It's a capacitor. I'm either just going to change it, or at least I'm going to test it for ESR and see if its ESR is high. There's some other ones as well, like on this power supply. You know, there's a capacitor. You see a capacitor in there, right there. I guess maybe I'll turn this away from the window.
Isn't it already too late when this has happened? Because everything that is connected to the power supply.
What about low?
And it gets
You mean the load is blown up at this point?
High voltage.
Yeah.
Could be. Yeah, bad power supplies could definitely damage the load, any load. You know, you can probably put 6 volts on the ICs on an older computer board and not have them blow up. But if it's putting 8 or 10 volts on them, it definitely might have blown those chips. You never know. But you need to look carefully because, for example, you know, you see a capacitor in there. You see a capacitor, you know, that guy right there. But look at the crazy place this designer put a capacitor. What the heck? Why would you put a capacitor between the fins of a heat sink?
It loves the heat.
Okay, it's the, okay, put the thing that doesn't like heat right in the middle of the heater. Really? You know, so you never know. So, I mean, what does that do? I don't know specifically. Could I test it? Yeah, I could test it to see if it's good or bad. So, be careful. Like the secondary side, people see the secondary outputs there and they go, oh, they're domed, I'm going to change those. But, oh, there's 2 more hidden there. What are those guys doing there? I don't know. Can I test them? Yes, I can. So really, I mean it. I'm just a parts changer. I see a part that I recognize. Could that be my problem? I don't know. Let's throw an ESR meter. Oh, not that. Let's move on. I told you I'm kind of in the casino business. And your 808 t-shirt reminded me of this. I'm in the casino business. And I was in the state of Washington, really close to the Canadian border. Like way up there. And I'm actually a Canadian citizen. Thank you very much. Way up there. It's like you get to Seattle, and then you drive 3 hours north through the snow and the big woods, and at the big pine tree, you turn right, and you go 6 miles, and you're on the reservation. And I'm out there, and I'm teaching a class, and one of the guys in the class brings me a power supply. It's a German, I can see it's German power supply. Hey, Randy, can you fix this? He hands it off to me, and I look at it, and I say, oh, what's this from? He says, it's from my mixing console, which is what your 808 reminds me of. He said, it's from my mixer. And I used to be a roadie, and I used to be a sound man at the Whiskey A Go-Go in Hollywood. I operated the sound machine, the mix. I did the mix, set the mics. Anyway, so he says, it's for my mixer. I have this $15,000 mixer and a home studio, and it's dead, and they want $400 for the power supply or something like that. Can you fix it? And I went, oh, sure, let's do it. So the first thing I did was tested it, and it had had a plug input, and I just plugged it up, and no output at all. And I look at it, and I see a bunch of capacitors, none of which look bad. Again, just because a capacitor looks good doesn't mean it's good. If it looks bad, it is bad. If it's domed or whatever, it's bad. But just because it looks perfect, so his all looked perfect. But when I whipped the ESR meter on them, they were all bad, like really bad, super high ESR. They had the capacitors in stock. We got the capacitors. I handed it off to the guy sitting right there. He threw in the capacitors while I was doing the lecture, tested it, works perfectly. Here you go, $400, $500, fixed with less than $1 worth of capacitors and in about 10 minutes. And that's what most of my repairs are. Most of my repairs are simple stuff like that. Electronic repair doesn't have to be real difficult. Sometimes, a lot of times, it's just finding a few bad parts and throwing them in. Very fast repair. And recently I had to do this on my home TV. My home TV crapped out. Popped out the power supply. Oh, high ESR. Threw some caps in. Fires back up again. Thank you very much. It doesn't take intelligence. It just takes wanting to do it, really. And being a cheapskate, not wanting to spend a bunch of money on other stuff, right? So it might be better to say bad caps cause voltage issues, right? Most of the time it causes low voltage, and in this case it did cause low voltage. The low voltage here caused it to raise the voltage over here. Now, here's a similar scenario. See if you can retain this, maybe not. Well, since we're looking at the 12-volt output, here. Sorry, I need to back up. I need to explain another thing. So there is another different kind of way that we do this. So one way that it's done is to throw a winding on the transformer that is a sample, and sample it and no. But there is another way, a more modern way to do this. There is another kind of a part called an opto isolator. It might be in your book. Let me just take a quick look. Anyway, stand by, please. Oh, I think it is, now that I think about it. Check. 63, please. Turn to page 63, 63, 63. Oh, wait a minute. Oh, no, I don't have an image of it here. Sorry, never mind. I'm talking about this, but it's a slightly different. Sorry, I thought I had an image of the thing. I'll show you in just a second. I want to introduce you to another part. This is not a failure item. I'm not Jump, honey, please. This is not a failure item. I'm introducing it to you because it's part of the circuit, so you know how it works. There is another way we can do isolation. We've been talking about using the transformer as isolation, but there's another way we can do that, and that's optically. There is another part called an opto isolator. It's called an opto isolator. And it consists of two parts, a light emitting diode and a transistor, a light operating transistor. So the opto isolator is a little box like this. There are just 4 leads on it. There are 2 legs on one side and 2 legs on the other side. On one side of the opto-isolator, there's a light-emitting diode. And it doesn't really look like this, but I'll just draw it like you're familiar with what an LED looks like. So that's that. It's really just the chip, the LED chip. On the other side is a part called a photo transistor. You guys here need to know about that because you got tons of optical stuff in here. I mean, just tons of it. So photos, from the Greek word meaning light, phototransistor is a light-operated transistor. The schematic symbol for the phototransistor, there's a regular transistor. A phototransistor is a transistor in a transparent package that instead of putting base voltage on it to turn it on, you just shine a light on it and it turns on. So the schematic symbol for the phototransistor, sometimes they'll draw a stub of a base in there, sometimes no base at all. And you see the arrows going into it, as I explained the first day of the class. When you see arrows going into a part, that's a light-operated part. When you see arrows coming out, it's emitting light. So on one side of this thing is the LED, and on the other side is the phototransistor, like that, right? And they're looking at each other. The inside of this thing is filled with transparent epoxy. So it's all sealed up, and those guys are like doing a staring contest. They're looking at each other for eternity. And that little opto-isolator is this guy right here. It's this little 4-pin integrated circuit that you see right where my bright light is shining. There you go. Everybody see it? The little 4-pin job right there at the bottom of the screen. Down there, right? So, once again, we pick an output. Once again, we pick one of the outputs to look at, in this case, the 12-volt output. And this time, what we're going to do is really look at the actual output. We're not going to make another sample winding over here that represents the output. We're going to look at the... Should I wait?
No, sorry, interrupting your lesson.
I hate you for interrupting my lesson.
Sorry.
Really exciting.
Yeah.
Okay, just keep it down, boys. All right, so we have this optical coupler. So the opto is hooked up here, let's say to the 12 volts. And of course, as you probably know, there's a resistor in series with the LED. And that is grounded. Notice it's the chassis ground. So that's the light emitting diode emitting the light. That is half of the opto isolator. The other half is hooked up to the voltage reference input. And I'm really simplifying the circuit a bit so that you can understand it easily. Notice that it has the earth ground, because everything on the primary has the earth ground. And here's the light coming into it. And that's the other half of this same device. So will you grant me, I think you will, that the higher the output voltage is here, the brighter the LED will be, of course. And if the voltage drops, it'll be dimmer. So this transistor
It's
is
kind of remote controls or non-wireless, non-wired controls. Yeah. So with lights. With lights. Yeah. Sorry, Randy.
whatever.
It's one.
So the way this works is that this guy is always looking at the LED. And if everything is perfect, it has a certain duty cycle, whatever the duty cycle is. Let's say, for the sake of discussion, that the voltage goes up and that thing goes a little bit brighter. The transistor sees that. When that gets a little bit brighter, it makes the transistor turn on more and lowers the voltage on the voltage reference. When the voltage reference gets lowered, it makes the pulses narrower. When the voltage reference goes down, it tells the chip to make the pulses narrower. So if the voltage has gone up, that gets brighter, it sees that, makes the pulses narrower, it brings it back down to what it should be. If the voltage was too low coming out here, the transistor sees that and says, yo, you're not so bright, buddy. You know, what's going on? Your voltage is dropping. And what it really does is causes the voltage reference to rise. as this transistor turns on less or turns off more, I guess, the voltage at the voltage reference input rises, and that causes the chip to say, hey, Mr. MOSFET, make the pulses wider and bring the voltage back up to what it should be. And again, same thing, it's not really going up and down, it's doing this 50,000 times a second. So this is a much more modern way to do it, way more reliable. It's way more reliable because we don't have to worry about that little capacitor failing, and we don't have to make an extra winding on the transformer. It's just a better system. But there is another thing that can happen that can be very confusing. Because we are now looking right at this output, what happens if these capacitors are going bad? Bad caps cause low voltage, right? If those caps are going bad, this thing's going to get dimmer, isn't it, right? What's this thing going to do in response? It's going to make the pulses wider, and it's going to shoot the output through the roof. And all of a sudden, it's going to bring it up until that averages 12 volts. But it's not really 12 volts. It's really 17 volts or something. It's going to bring it up until it seems to average 12 volts. But the 5 volts is all of a sudden going to be 7.5 or 10 volts or something like that. And these caps, which are bad, are really, when you measure it, you might measure 12 volts, but it's really going 16.6 or something like that with a whole bunch of ripple because of the bad capacitors. So there's another reason or another way that a bad capacitor, which initially causes low voltage situation, can cause other voltages to rise. So bad caps do cause low voltage, but they can cause lots of other crazy things to happen. In this case, cause the voltage to increase. Does that make sense to everybody? Yeah. But we're still looking at bad capacitors, aren't we? We're still looking at capacitor failure, which is the first thing you should be looking at. In a switch mode power supply, generally speaking, unless it's blowing a fuse, one of the first things you should be looking at is really all the capacitors. You know, starting with the output filters and all the rest.
If you put zeros behind it that protect the load.
You are not modifying anything.
I know, but if you would see it as design, would you see design where you have the zeros behind the 5 volt?
Well, the problem with he's asking, can you just hang a zener on something and keep it at 5 volts or whatever? The problem is that when the error occurs and the voltage tries to rise, the zener is going to try to hold that down, and it's just going to burn out the zener diode. Okay. So you generally don't put in parts to correct for some other part failing. Okay. That's just not, you make the design so the part doesn't fail. Okay, and then finally, there's one more thing to look at, and I think you asked the question, Philip. Somebody did, or Alexei, I would say. Where does the PWM controller chip get its power? It has to get power from something, and this is another possible common failure. Possible failure that's pretty common, I guess. Better way to say it. Very often, the PWM controller integrated circuit, or the circuitry, is driven off of a winding on the transformer, just like the sample winding, and sometimes it is the sample winding, where they put like a 12-volt winding on there, they turn it into DC, they filter it with a filter capacitor, like that, and then, let me just erase that just to get it out of the way. And that is what is used to power the integrated circuit. The power is sometimes referred to as V sub CC. I don't know why. The actual power itself that powers the chip. So it's really kind of self-powered. The chip itself is powered by a winding on the transformer. But wait a minute. That voltage doesn't exist until the power supply is already up and running, does it? That power supply, there's nothing's going to come out of any winding on the transformer until the MOSFET has clicked on and off at least once, because we have to get it going. So how can it possibly power itself to turn on the MOSFET when there's nothing coming out of there? There's a kickstart circuit on lots and lots of these power supplies, especially the arrows that you're working with here. there is a circuit called a kickstart. And I'm referencing a motorcycle kickstart, where before they had electric motorcycles, you kick it to start it. Let me just move the capacitor over here. And the way that works is pretty interesting and a fairly high failure rate thing. So wake up, I know we're ready to go home, just wake up, and this is the last thing I'm going to show you. What they will do very, very often, and it's a thing that fails, is they'll take some of this 165 volts or 320 volts in your case might be, and run it through a very high ohm, high wattage resistor. It might be 120 kilo ohms or so. Sometimes they put a couple of them in series even. 120K, a bit, and it might be 1 watt or 2 watt, just to show you. Let's see if I can find it. Oh, sure. It's right in the middle of the power supply. And this one's 150K, it looks like. 150K. This big, high wattage, that's got to be 2 watt at least. Maybe it's 5 watts even. Let's see if I can find it on some other power supply. Oh yeah, here it is.
That's the one with that special heat resistant paint?
Yes, that's a non-flammable resistor. Anything that's 1 watt or 2 watts is going to be a non-flammable resistor, a metal film resistor or metal oxide resistor. And then a capacitor like this. But in this case, the capacitor is not a filter capacitor. This is really very interesting, I think, anyway. So we have DC here, and of course this takes DC to operate, but this voltage is way too high, it's 165, and this chip only needs like 15 or 12 volts or so. So they'll run it through a resistor to cut it down, and then run it through a capacitor. The capacitor is not a filter capacitor. The capacitor is in series with this. Well, remember I mentioned earlier, you probably don't remember, that capacitors block DC. They block direct current. So even though I've lowered the voltage here, whoa, wait a minute, isn't that capacitor going to block it? It does block continuous DC, but when you first apply power to this thing, that capacitor is fully discharged, of course, before it turns on. You will get one momentary pulse through that capacitor. When you first turn it on, and that's your kickstart pulse, when you first turn it on, one little pulse will come through, and that's enough to start the PWM controller. It makes the MOSFET go, and now we do have 12 volts coming out of here, which we rectify, and then it takes over and powers the chip. Okay. But it has to be kick-started first. And there are 2 common, super common failures here. Typically, that's like either 10 microfarads or 100 microfarads, some itty-bitty capacitor. And capacitors do something called leaking. Capacitors can become what we call leaky. It is not a dead short, but it's where it allows some current to go through when it's not really supposed to. It's supposed to block DC, but allows a little tiny bit through as it starts to fail. Now we're drawing continuous current through that 120 ohm resistor, 120 watt resistor, 120 kilo ohm resistor, and it gets real hot. And then eventually it opens circuits. And once it's open circuit, the power supply won't work anymore. And the weirdest symptom of all is the kickstart circuit is only used once when you first turn the game on. If the game is on 24/7, if you never turn your games off, that kickstart never is used again. The power supply might work perfectly okay for years, and then if you turn off your power and turn it back on, now the power supply is not working. And you're thinking to yourself, something I did blew out the power supply. Turning the power on and off blew out the power supply. It didn't. The power supply was bad way before you turned off the power, but you never saw a failure because that's only used when you first started. So there are 2 parts that you need to test. One is this capacitor. Common failure. How do you know which one it is? You don't. You test them all. You test all the little capacitors. Never fail to test any capacitor in anything you're working on. You have an ESR meter, it's easy now. Don't depend on your eyes. And now, as an experienced technician, where as a beginning technician, you're drawn to the big capacitors, they're domed. Ooh, I can see that they're bad. The first thing I do is go for the itty bitty teeny weeny ones. And I check those, and for sure the ESR is real high, like on that mixer panel I just told you about that story. The ones that were bad weren't the secondary filter caps. They were all perfect, thousands of microfarads. It was everything in the startup circuit, like three, two 10 microfarads and a 100 microfarad or something. And that's all it was. It was just those itty bitty ones. So don't fail to test the little ones, just do it. It isn't very difficult. And the reward, when you can go right to those things, go, oh, they're definitely bad, and pull them out and put them back in. Even though I've done this repair hundreds of times, thousands of times probably, I still do my little dance in the underpants when I fix it. I just think that it's wonderful to be able to fix stuff, especially if you can do it just by tossing in a few cheap parts, really, So anyway, so this is called a switch mode power supply. And those are the things that's how it works, and those are the things that generally go bad. Tomorrow, when we start looking at the whole monitor schematics, I'll show you the schematic in the monitor itself. We won't do that. And we'll trace the current flows and all that kind of stuff, and then we'll move on to the other monitor circuits, and Bob's your uncle, right? And we'll be done. So that's it for today. Does that make sense to everybody? Everybody cool? All right. Okay. Hasta la pasta, and I'll see you tomorrow at 9 o'clock.
te kijken of ik de tuning langzaam maar zeker capture ready kan krijgen.
Ja, precies.
Dat is een plus.